Du-du-du. Okay. Okay. Hope the stream's up and running. Apologies for my slight nasal voice cold. Got a cold. I think I don't know, but we'll roll with it. So what is the aim today? Well, it's going to be like yesterday. So this is going to be a another revision stream for the paper two tomorrow, based on the sort of, I guess, predicted topics, the topics that are very likely to come up, right? Based on what we've seen on paper one. So these are your, I guess I'll just write it here. Linear transformations. That's going to should definitely come up, I reckon. Your vectors, your proof by induction, your polar coordinates, your coupled first order ODEs. I know you were asked to, this is for Edexcel, by the way, but I hope this revision will help with other specs. But for Edexcel, obviously there were two differential equations, but normally they love asking for a coupled one as well. Normally like three differential equation questions, so we're missing one. We're expecting one to come up, right? And I expect coupled will come up. And so what else do I reckon? Series, more specifically the standard results, right? So the ones that are some of our squared, some of our cubed, stuff like that. I also predict Argand diagrams and roots of polynomials. I am aware, I think both vaguely came up, was it? A triangle question, was it? But I think they will come up in their own right in this paper, right? And like I said, multiple topics can repeat, I guess. But I think they'll ask a distinct question. So Argand, so specifically your loci, and so your circles, your perpendicular bisectors, so stuff that looks like this essentially. So, uh, stuff like x minus a less than x minus b, the modulus. Mod of x minus a is less than r, and your half lines, right? Your arg z is less than or equal or greater than uh, an angle theta, right? So those I predict they will come up in some way. So Argand diagram, roots of polynomials. So either roots of polynomials, either perhaps I ask you something about shifting polynomials when you're given like a root, like 2 alpha minus 1, 2 beta minus 1, and 2 gamma minus 1, asking you to create a new or come up with a new polynomial by using a W transformation, right? Um, or they might ask you some stuff to do with like the sums of the roots and the pair products, and like the products and stuff like that. So they're it's sort of like how that relates to obviously like the coefficients as well. So like minus b over a would be the sum of the roots and so on and so on. So they might actually do some stuff with that, and we'll look at stuff like that later. Uh, how many topics are here? 1, 2, 3, 4, 5, 6, 7, 8. What's the other one I was going to say? Uh, oh, I left my brain now. Oh, Maclaurin series. There we are. That I think there'd be just a little question in Maclaurin series. I've not seen many bad questions on this, so hopefully it shouldn't be too bad. Just a little question on that. I don't have a question on it today, purely because I want to get through the main topics and the major mark questions today. But I did go over it yesterday, and if I have a time, I guess I'll look at one of the Maclaurin questions. But there'll be a little question on that, I reckon. So whether you need to differentiate multiple times to form a Maclaurin series, or use standard ones like e to the x or sin x, and for example, create new ones. So the Maclaurin series of e to the sin x, you're going to have to substitute the Maclaurin series of sin x and then replace that with, instead of e to the x, it's like e to the like x minus a half, a third x cubed or something like that, or sixth, I should say. And then you replace this in replace for x for e to the x, and then you do some stuff like that. So something like that. So either you combine and compound known series together, or you come up with your own by differentiating. But it shouldn't be, if you revise it, hopefully it shouldn't be too bad, right? And that's really all. I guess potentially they could ask matrix modeling, um, or something to do with systems of equations, because obviously they asked for determinant stuff, didn't they, in the first paper, or potentially even hyperbolic, so hyperbolic integration, stuff like that. So what substitution do you use to evaluate something like 1 over 1 minus x squared? But I won't have time for that. But I think they did ask a lot of integration, and I think there was a hyperbolic question in the first paper. I don't know, but these are the main topics I've revised, right? And they can make a paper based on these, right? There'll be 75 marks worth of content here, which will. And so what I've done with this stream and the aim for this is actually to come up with questions on these topics, right? Almost formulate a predicted paper in a way. So the questions based on the topics are compiled, varies from the past papers to have a look at, and hopefully this will be a good revision. And also, just to say as well, just before we do start, I was really blown away by the attention the last stream got on YouTube. Anyway, 121 views. That's by far the most I've ever got. So I hope they're useful. Yeah, I think yesterday could have gone better. Again, I will say again, I'm still new to this. So I do apologise, a bit rusty or whatever, whatever. But I'm just, I don't know. I'm trying with what I can work with, do the best I can. But hopefully if it helps, it helps. Anyway, I'm going to stop the rambling and I'm going to start. Yeah. So this is the first question. I'll leave this here, this predicted topic. I'll write it here, predicted topic. That's not part of the question here. Okay, so predicted topics. So let's have a look at this first question here. So it's a transformation question, and it's about invariant lines. So it says the matrix A represents the linear transformation M. Prove that for a linear transformation M, there are no invariant lines. So let me just copy. Hang on a second. There we are. So let me just copy the matrix we have. So A was what? Sorry, what was A? 4 minus 253. Now I did an invariant line question yesterday, but I'm doing it again today. See more questions like this. Hopefully, you become more comfortable. I reckon they might ask about invariant lines and stuff like that, so I think it's good to do it. And there's not a lot of information in the text. Well, no information in the textbook that I'm aware of. Actually, it's quite bad. Actually, if it's on the spec. So I thought I'd go over it now. So I'll go over it again. So yeah, so the question yesterday was looking at finding invariant lines. Now we're proving there were no invariant lines, but you'll see it follows the exact same methodology. So hopefully this will help if the question like this comes up. So let's jump in. Okay, uh, so what is an invariant line? So essentially, invariance. Well, there are two cases you need to look at. Two parts on the spec anyway. Either invariant points, which remain the same, so they remain in the exact same place after you apply like a matrix transformation. So say we had a times a point xy, and then we you get the same point back. That is an invariant point, okay? But you could also have invariant lines, okay? So what that is say we have a line here. So you have a line of points. Well, a bit curvy, but you know what I mean. And so if we then apply transformation, this line will stay exactly the same. So invariant line means same gradient and y-intercept, because obviously those two things define what a line is, right? A line has a gradient and a y-intercept. Uh, but that does not mean every point on the line remains the same. As long as all the points remain on the line after the transformation, after we map every single point on the line by transforming it, they can still move on the line. So say this point here, after the transformation, it can still move down this part here, still on the line, but it's moved down it, right? Like with this point here, this point can move up further along the line up here. But the point is, obviously, they move, so the points themselves do not need to be invariant, but they still remain on the line. So all the points still remain on the line, but they can still move positions, right? But the whole idea of an invariant line is that the line itself stays the same, okay? So for that to happen, it has the same gradient of y-intercept. So what does that mean? Well, if we transform, so a general transformation, we say times a matrix by a point. Now, a general point on the line would be x and mx plus c, because obviously y is mx plus c. That'd be a general point on the line, or the general line, right? Mx plus c. And if it's invariant, like I said, the line has to stay the same, so the same gradient of y-intercept, but the point doesn't stay the same. So the point, the x coordinate can change. So x dash is the transformed coordinate of x, so it's different. But then the y coordinate, mx plus c, well, m x dash plus c, okay? And that's the idea, right? With this sort of question. So the gradient and the y-intercept c and m remain the same, but x, the point itself can change. So we do a dash to show it's transformed, okay? If, however, the point was invariant, it would have xy, and that would have to remain xy. But here the points are changing. It's just that the y-intercept and the gradient remain the same because it's a line, not the points themselves. Okay. So now we want to investigate this. And if you watched yesterday, it's the same sort of thing. You just plug this sort of thing in, and then you find some equations, and then we go from there. So let's expand this. Let's do some matrix multiplication. So that's going to be 4x minus 2mx minus 2c. That's going to be the same with x dash. And then you're going to also have 5x plus 3mx plus 3c. Oh, hang on. Yeah. And that's going to be equal to mx dash plus c, if you just compare the components, right? Okay, now essentially, well, the simple size equation, so we can substitute one to the other. Well, we have x dash here, so I think we can substitute it for x dash in the second equation. So let's do that then. So I'm going to do it, no, let's do it here. So I'm going to say 1 and 2 here, I guess. I'm going to say sub 1 into 2. Although you don't have to write this, but it makes it clearer. Now I'm going to write it up here. So that would mean 5x then, plus 3mx plus 3c. Has to be m lots of x dash. So times the whole first equation by m. So you get 4mx minus 2m squared x minus 2mc plus c, right? And that's our equation, right? So that's what we can deduce. Now, let's rearrange. So let's put x on the variable bit, right, on the left side on its own. Let's put it in terms of x. So x of 5, if we factorise it out, 5x minus 4m. Yes, plus 3m here because there's another x. Plus 3m minus 4m plus 2m squared. So that's all the x terms, and that's going to equal uh, and that's going to equal. I'm going to put it down here a little bit, the right hand side. So the non-x terms of 3c minus 3c because it's going to the right, minus 2mc plus c. Okay. So then we can simplify this a little bit. X of 2m squared minus m plus 5 is equal to minus 2mc minus 2c, right? Okay. Cool. So what can we deduce? Well, actually, rearrange it on this side, right? Put this all on the left. And actually, you should notice a particular form when we get this in. There's 2mc plus 2c equals 0. Is this not an equation of a line? So this is, if we call this big M, and we call this big C, is this not in the form mx plus c equals 0? Okay. Now, we essentially need to consider when this can be 0. Now, you cannot you cannot do anything with x here. X varies, so you cannot set x to anything. I guess you might be inclined to say if we just rearrange the equation at the top, if we then said x was minus 2mc minus 2c over 2m squared, so we just divided through to rearrange for x. That we can't do that, right? Because x can vary, so we can't set it to be a constant here. So that's not the way to approach this. So if we can't touch x, how can we still set this to be 0? Well, every other component has to be 0, right? So if we say x of 0, so say this is mx plus c equals 0, well, x, we have to leave it as it is. So that means m has to be 0. So then you have m is 0. So then you'd be left with c equals 0, right? 0 plus c, 0. That means c also has to be 0. Okay, in order for this to be 0, no matter what x value we pick. Okay. Okay. So that's what we're going to do. So the both components essentially have to be 0 for this to happen. So that means 2m squared minus m plus 5 is 0. We'll do this bit first. So what happens here? Well, notice the question's asking us to show there are no solutions. Well, let's try and solve it then. 2 might put this in the calculator, and actually you get complex solutions. So what this says is discriminant is less than 0, right? Which means no, I guess real solutions. But obviously m can't be complex, right? We're not in the complex plane, right? So there are no real, I guess, solutions. Okay. So then let's look at the other case. C is 0. So this is when m is 0, by the way. That's the first case. Let's look at this part then. That means 2mc plus 2c has to be 0. Well, we can factor that out to say c of 2m plus 2 equals 0. Okay. You have c 0 or m is minus 1. Uh, but actually, both of these have to happen, right? M has to be 0 and C has to be 0. So C0, sure, can be a solution. So why would then, so if C0, why would it have to be MX for some gradient M? But actually, look here, this has to be fulfilled as well. M has to be 0 here as well for this equation to hold true for any X. But we can't have any value of m. But when m is 0, the big M, or the first part, But I know, so not wow, it can't be m is 0, but m cannot be 0 for any gradient m. So there are no solutions to this problem. So there are no values of m to give an invariant line, right? Well, a line has to have a gradient, so really this is essentially just saying there are no lines, there are no solutions, so there are no invariant lines. So there are no possible invariant lines under the transformation. Okay, because obviously then if you pick the other case, m is -1. Well, like I said, for any value of m, the first part, this if you look at this bracket here, that cannot be 0, so therefore this equation cannot hold. Okay. So no matter what solution you get from C0, so if you pick C0, it doesn't matter because M, you still have to have a gradient, right? But you can't have a gradient. So really, it fails. So there are no possible invariant lines here because of the fact you get no real roots, okay? No real solutions for M. Okay, so that's that question. So that's the methodology, essentially. Once you write this matrix out, then hopefully it should follow from there. So just realise an invariant line means the same gradient and y-intercept, so they keep m and c the same, but x, the point itself, x can vary, so we need to introduce x dash. Okay, so that's how to find and deal with invariant line questions. So hopefully they come up in this. Hopefully that should be okay. But let's move on to the next part. Okay, polar coordinates. Okay. I like this question because it assesses basically everything in one. So every part of polar coordinates is assessed here. Tangents and areas and sketching as well. Okay, so we're given a curve which is r is a of p plus 2 theta. A and p are positive, p greater than 2. There are exactly 4 points on C where the tangent is perpendicular to the initial line. So you need to hit perpendicular to the initial line, right? So that's going to be crucial. And then we need to find range of possible values, right? Which is in this. We need to show that. Okay. So that's going to be our point, right? That's going to be our a starting point, I guess. Is to consider perpendicular to the to consider tangent, I guess, perpendicular to the initial line. Okay, so as a rough sketch of what's happening here, so we have a curve, a polar curve, I don't know, something like that, right? I don't know. Obviously, that's the starting point, and that's the initial line. So a perpendicular to the initial line obviously has to be straight and vertical because it's perpendicular at 90. And to the curve, well, it's going to be looking like this, right? There and there. Something like that, right? So what that means is essentially also if you essentially consider the fact that really this is just a way of representing x and y coordinates because if you know a general coordinate, right? Say this is the origin, right? Which is here, right? The origin in a way. If every x and y point, x, y, there's a radius, right? There's a distance r, which is the distance we use for polar coordinates, and an angle theta. So really, the ascent really in a way the initial line is kind of the x-axis, and then how far it goes up is almost the y-axis. And then how far it goes up is almost the y-axis. And yeah, so really this is just a way of codifying x and y coordinates, and it kind of reflect, and it should look kindly, acts vaguely in the same way. Polar coordinates as Cartesian. So I guess that the initial line is akin to the x-axis, and obviously how far it goes up and down is the y-axis. But obviously instead of that we're measuring angle, so we're representing the same thing, but instead we're measuring angles and radius, right? Instead of just how far along it is, up and down and left and right. So why am I saying that? Well, a tangent, well, it's perpendicular to the initial line. So if we kind of treat this as the x-axis, we are saying dx by d theta has to be 0 for a tangent perpendicular to the initial line, because there are no changes in x values along this tangent, right? This tangent, x is fixed, remains the same. So x is a constant here, x is k. Obviously, if you differentiate it, it will go to 0, which is what's happening here. So for any tangent perpendicular to the for any polar curve perpendicular to the line, the dx by d theta has to be 0, right? Instead, alternatively, they might ask about it being parallel, but in a similar way, the y isn't changing, right? The height, the y isn't changing, so that would be dy d theta is 0 if it was parallel, but instead we're looking at perpendicular tangents, so the x coordinate essentially will stay the same. So dx by d theta is 0, and it won't be dx by dr, because remember, essentially it's all expressed in terms of theta. R is in terms of theta, uh, and x is in terms of r cos theta. But then r is in terms of theta, so essentially they're saying you're multiplying two functions of theta essentially. So that's why you differentiate theta and not r, okay? Because r is essentially a function of theta, so that's the reason behind that. But we are going to use this actually. Well, we know in general, let's go back to our triangle points here. Any general point xy has r and theta. So using basic trigonometry, hopefully you realise by now x would be opposite over x would be, well, that's the adjacent, so that would be x is r cos theta if you use trigonometry there. But hopefully you should remember that by now if you revise polar coordinates. But that's how you get that. And obviously y would be r sine theta because y is opposite of facing the angle, but x is adjacent to the angle, so cos theta. Anyway, but we're interested in x is r cos theta. So actually got x in terms of theta. So then therefore, actually let's substitute r in. We are given also r is what? Uh, oh, a of p plus, okay. A of p plus 2 cos theta. So actually, let's substitute that in. So x is for r, that's going to be a cos theta of p plus 2 cos theta. Let's expand that. So it's going to be AP cos theta plus 2a cos squared theta. Okay, well, we've got that's x. We've got to do a bit more with that. Now we want to differentiate x with respect to theta, obviously, as we discussed, to get the perpendicular tangent. So dx by d theta, that's going to be, well, cos differentiates to minus sine, so you'd be minus ap sine theta. And then plus, then we use the chain rule there, so cos squared. So if I say this is the same as cos, just rewriting it, cos all squared, that hopefully make it clearer where the chain rule is. So plus 2a, bring the multiplier out, and then we differentiate this. So this is going to be 2 times the power times by the derivative inside, which should be minus sine theta, and then you're going to knock one off the power, so it's going to be just cos theta, right? Because 2 minus 1 is 1. Okay, so that's the derivative. Let's now simplify this. Minus ap sine theta minus 4a sine theta cos theta. And this has to be 0, right? As dx d theta. So really all we're doing now is solving a trig equation. So we get, well, I note sine theta is on both sides. And also no a's on both sides as well, actually. So a sine theta of minus p minus 4 cos theta is equal to 0. Uh, yes. So therefore, well, a sine theta is 0, so sine theta essentially has to be 0. Or uh, uh, 4 cos theta has to be minus p. Therefore, cos theta is minus p over 4. Okay. Well, well now essentially we just have to solve this, right? Let's look how it happens when we solve it. So sine theta 0 should be easy. Again, I guess we want to consider the graph. Sine it. It's 0 between 0, pi, and 2 pi, and then so on. But let's look at the let's look at the interval we need to work in, right? It's between 0 and 2 pi, but it cannot be 2 pi here. It's not equal to. So actually, our only solution here is going to be, for sine theta 0, it's going to be theta is 0 or pi. So there are two solutions coming from this. And it's told us there are exactly 4 points. So there are 4 solutions. So two solutions from sine theta is equal to 0. And there are 4 solutions in total. Therefore, because and you might think, oh, what about if maybe they are the same angle? That can't be true because what makes every point unique on the polar curve is that the angle's unique. Obviously, they repeat every 2 pi because obviously that's how it works between 0 and 2 pi, and then it just goes. Usually repeats anyway. It doesn't have to. Depends on how the curve's defined. But because we're working between 0 and 2 pi here, the angle will be unique to every point on the curve. So if there are 4 different solutions to theta, there will be 4 points, right? So there has to be 4 solutions for theta here. Okay, so there are 4 solutions total, and they take 2 away. So therefore, 2 solutions must come from cos theta is minus p over 4. Okay, so let's study this. Well, let's look at the cos curve. I think that's the easiest way to look at this. So that's 2 pi, and that's 0. So what values of y equals cos theta ensures we get 2 solutions in this interval. Um, Actually, make the sketch a bit nicer. There we are. Well, clearly when it reached the peaks, right? So when y is 1 or minus 1, you only have one solution. So that means minus p over 4 can be equal to 1 or cannot be equal to minus 1. Okay. So actually, really, it's between what minus p over 4 has to be between minus 1 and 1, right? Because if it's between minus 1 and 1, if you draw a line here, any line, it's going to cross the graph twice, right? The only time it won't cross the graph twice is when it's at the peaks. Okay, and obviously, like I said, 2 pi is not a solution here, so y cannot be 1, and it cannot be minus 1. So it has to be between strictly minus 1 and 1 in order to guarantee us 2 solutions in the range. Okay. Now, the last thing we need to check is we need to check that there are distinct solutions from sine theta 0. So we need to check uh, for any value of these p here that sine theta cannot be 0. Well, the easiest way to check that, we need to check theta essentially are not solutions. Because if they are, then actually we have an overlapping solution. So that means we only have 3 or 2. We need 4. So the all solutions here, the two solutions, and we will only have exactly 2 here. They have to be distinct from sine. Okay, so the angles. So check. So the way to check this essentially is to substitute 0 and pi into cos theta. And let's see what happens. So cos of 0, cos of 0 is 1. And actually cos of pi is -1. But we discussed that minus p of 4 cannot be 1 and minus 1. So we don't need to worry. So we are, minus 1 between minus pi of 4 and 1 is still valid. In order to give us 4 exact solutions. So there are no, so they are not solutions. Yeah, and that's it, right? So now we've verified that there are, this gives us 2 exact solutions. Distinct solutions, exactly 2 solutions. Cos theta is minus p over 4. When this holds, and we have also given, and we've also ensured that they do not overlap with the other solutions, right? So they're all distinct, okay? So therefore, we have this inequality, right? -1 minus pi over 4, p over 4, sorry, and 1. Now we just want to get for p, so that would mean, well, -4 would be between minus p and 4. So then we essentially reverse it. So we can split this up. So we could say -4 is less than minus p. So that would mean 4 is greater than p. And minus p is less than 4. So p would have to be greater than -4. Which then means p has to be less than 4 as well if we rearrange that. So really, to ensure perpendicular, to ensure what we're saying, for exact points that are perpendicular, right? So perpendicular to the initial line. We need p is greater than 4 and p is greater than -4. But however, uh, so we can write this as -4 between p and 4, right? So p has to be greater than -4 and p is less than 4. However, they told us in the question that p is greater than 2. So we need to actually get rid of this and tighten the bound. So that actually p has to be between 2 and 4. Which is what we need to show, okay? Um, so yeah, that's really that's how you tackle that. And actually, it's very, 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 very reminiscent of the proof you need to learn for proving when there's a dimple, which is when you consider like so if you have to form p plus q cos theta, which is what we've got here, you have a dimple if p over q or the modulus is less than 2. So p has to be less than 2q. And that's very reminiscent because it's essentially considering when there are three tangents to the perpendicular. So you need to consider dx by d theta is 0. And you get this case here of cos theta will be minus p over 4 or 2. Can't remember. And yeah, it's the exact same reasoning and it follows the exact same type of proof in the textbook that you need to learn. But that's how you go through this anyway. It might be a little bit like, I guess, arduous. I guess you have a bit, you have to think a little bit maybe, but hopefully that's clear. So essentially, I guess to wrap this up, to answer that question, dx by d theta, you have to set the dx by d theta 0 because it's perpendicular, so the x coordinates are not changing; they stay the same. So that has to mean obviously the gradient with respect to x isn't changing, it has to be 0. And then essentially you are just doing a differentiation exercise, right? So if you substitute x with r cos theta into the equation, then you differentiate it set to 0, you solve it, and you get this. So then you essentially just need to consider when you get 4 solutions. And then sine theta 0 should be easy enough. And then cos theta is equal to this. You're going to need 2 solutions in the range of 0 and 2 pi. So essentially, it has to be between -1 and 1, which is where this happens. And then you do some stuff to then show p is between 2 and 4. Hopefully, that shouldn't be too bad now. Okay. So then part B, what's it saying now? It is asking to sketch the curve in the same range of a of 3 plus 2 cos theta. Okay. Obviously, if a graphing calculator, you can cheat this question. I'm not sure for that reason. I don't think they like asking you to sketch a polar curve because they are aware people have graphing calculators, and it is a bit unfair for those who don't. But we'll go over it anyway. So the sort of process. I believe there are certain curves you need to learn to draw, and actually one of them, because I did look this up before, is in the form, as we just discussed actually, p plus q cos theta. And it works how you think it does. So when you if you pick certain values for theta, and that's the general idea with sketching polar curves. If it's between 0 theta and 2 pi, and the angle is just theta, then you just consider, well, 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? So then r here, substitute r is 0, you get cos theta, cos of 0 is 1, so you're left with 5a. Pi over 2, again, you can use the cos graph actually that we just drawn up there. So then pi over 2 would be 0, cos of pi over 2 would be 0, so it'd be just 3a. Cos of pi would be minus 1, so 3a minus 2a would be just a. 3 pi over 2 would then go back to 0, so that'd be 3a again. And 2 pi would be 5a. And it's kind of symmetrical, right? So, no. Have an initial line, right? Always draw an initial line. Mark that. And use these values to guide us, right? So 0, when the angle's 0, you want it'd be 5a. Then when it's pi over 2, so essentially it's almost like complex numbers. You move the line according to the angle. So the angle you move away from the initial line, or the real axis, or the x-axis. That's where you mark it R. Okay. So pi over 2 is obviously 90 degrees. So we move 90 degrees counterclockwise. So at 90 degrees, it's 3a. So uh, if that's 5a, then 3a would be down here. And then pi, which is on the other side, it will just be a. So it will cross there, a. Then 3 pi over 2 again would be 3a, matching, and then it would go back to 5a. So in a way, it would look like this, right? But there's one. But there's one key difference. Not key difference, but there's one key thing to look out for. So that's the general principle for sketching a polar curve by plotting the r values against the theta. Um, if you have 2 theta or 3 theta, you need to double the amount of angles you consider. So if it's 2 theta, you'd need to consider 0 pi over 4, then pi over 2, then 3 pi over, no, then 3 pi over 4, then pi, then 5 pi over 4, then 3. So you need to basically split it all in half, so double the number of angles to consider, because when it's 2 theta, it can change midway through. So, for example, say if you had 5a to 3a, so it might look like this, but say if you had 2 theta, it could essentially have a different trajectory to what you expect. So it could be like that, and then it would rebound. Oh, that's horrible. So it could rebound like that, and then it could I don't know, do something like that. Something like that. I don't know. Essentially, like instead of like a smooth curve going that way, it could like go. It could go further outwards or inwards because the value might change to what you expect. But if it's just cos theta, it's a normal angle. Just consider like the different parts, right, of the graph. So 0, pi over 2, pi, 3 pi over 2, and then 2 pi again. Okay. Okay. So I waffled a bit there, but that's the main method. The key bit I'm going to get to it now is what I just discussed earlier. Actually, you need to consider with this curve uh, whether there's a dimple when it's pi. So it could essentially almost, you might expect it to just look like that. Obviously, it's a bit rough, but almost like a weird circly egg shape. I'll draw that again. Something like that, right? But you need to consider when it's a dimple. So it's a dimple when this form here, when P over Q is less than 2, no, greater than, no, less than 2, or equivalently P is less than 2Q. But have a look here. R is a 3. It's in this form because if you expand it, you get 3a plus 2a cos theta. This is in the form where we need to consider a dimple. And again, that arises due to the fact there are more than two tangents, right? If it's just a circle shape, obviously the tangent perpendicularly there and there. But a dimple shape would look like this. So there'd be one there, there'd be one there, and one there. And actually, it gives us a hint in the question because there are, I believe it's said, didn't it? There are there are 4 points that are perpendicular. Well, if there are only two tangents, if it's just a circle shape, here, that would only be 2 points. But if you have a dimple shape, like I just said, drawn, what is that? Like that, it's terrible. But you have one there, that'd be at, oh, God's sake. One there, that'd be at 1 point. Here, that would actually be 2 different points, here and here, and then the further point there. So there are 4 points that are perpendicular. So that tells us actually our curve must have a dimple in, not like a smooth, like circly type shape. It has to cave in and be a dimple. And we know this is true because P is 3a, so the ratio 3a to 2a is equal to 3 over 2, which is clearly less than 2. So we need a dimple. So essentially, it draws like you expect. So go from 5a to 3a, and then it goes to a, but it's going to have a dimple. Okay. There. Except I can't draw. There we are. Almost like a weird heart shape. I don't know. That's the best I can draw. But obviously, say it goes through the main points: 5a, 3a, 3a, and then 5a again. Um, but obviously, it caves in, so it forms like a little dimple shape, right? So there you are. Weird, I don't know, a weird hearty type shape. But yeah, so that's the graph, right? That's only for 1 mark. Hopefully that sort of graph sketching is clear, right? I think there are certain polar curves that you need to consider. So, for example, this one, like I said, you need to consider whether there's a dimple. I think there's another one where it's like with like petals on it. I can't remember what it is. It's like is it a sine n theta? So, and then what number n is, the multiple of n, determines how many petals there are. I can't. I don't remember that, but there's certain shapes you need to be aware of, and that's one of them in the form p plus q cos theta. Unfortunately, you just have to learn that right. Obviously, if you've got a graph calculator, then yeah, a bit easier for you lot. But yeah. But anyway, that's the 1 mark. Okay. Then it's telling us John digs a hole in his garden in order to make a pond. The pond has a uniform horizontal cross section that is modelled by the curve with equation this. Okay. The depth of the pond is 90. Water flows through the hose pipe at a rate of 50 litres per minute. Given that the pond is initially empty, determine how long it will take to completely fill the water. Okay. So essentially, we have a pool here that has the same shape or the same surface as this polar curve, right? And therefore, it has a depth of 70. So it's kind of like the pool has this sort of structure. No, not like that. Try and copy the curve again. Why can't I sketch? What's wrong with me? I can't sketch. Uh, oh, come on. I can do better than that. Okay. Something like that. Oh, God's sake. Okay, let me try one more. Okay, I don't know. So, it doesn't look symmetrical. That's terrible. Oh, for God's sake. Okay, something like that then. Okay, there's a dimple in the middle. So it has this surface, and essentially, uh, it, there's a depth of 90 to the 70 to the bottom, and it was 70 centimeters, was it? 90. Okay. So the depth is 90, and it has this surface, and it goes all the way through to the bottom. So essentially, the volume will be the surface area, surface times the depth of 90, right? That'd be the volume, how much water you fill in the pool here. So it's almost like a prism. So the cross section times the depth, right? So that's essentially what's going on here. So that's how you work out the volume. But then the question is, how do you work out the area? The area of this surface here. Well, isn't that just the polar integration to find the area of the polar curve? No. So isn't the area just found by doing a full between 0 and 2 pi, the full 360 of the curve, right? So we find the whole area of the curve, which is the area, the surface area. So we integrate over the whole 0 to 2 pi. So then area, if you remember in general, the area is, and it's in the formula book actually, let me get that out, to compute polar integrals. Um, where is it? Here it is, area of a sector. Uh, it's this in polar coordinates. It's this. It says sector. Uh, it just means the area of a piece of the polar graph, right? So between two angles, this is the area in polar coordinates. And that's what we're going to do. So we just have to use this formula. So it's going to be half of the integral between obviously our angle. So it's going to be the full 360, 2 pi. So between 0 and 2 pi of r squared d theta. Now we know what r squared is. So it's going to be between 2 pi and 0. Well, r, we are told, is, in the question, 20 lots of 3 plus 2 cos theta. And that's going to be all squared d theta. And so essentially, our problem now just boils down to working out this integral, which is normal math stuff, really. So that's going to be of a half of between 2 pi and 0. 20 squared, which is 400, I believe. Okay. 400, and then we're going to expand this bracket out. So 3 plus 2 cos theta squared, that's going to be 9 plus 12 cos theta. 3 times 2 is 6 times 2 is 12. And then plus 4 cos squared theta, d theta. I don't like having constant multipliers inside, so I'm going to do 400 over 2, which is 200. Bring the 400 out, which is what I've done here. Between 2 pi and 0. Of 9 plus 12 cos theta plus 4 cos squared theta. Now, theta d theta. Now, we can integrate a constant and cos theta quite nicely. You should know how to do that. But cos squared, not exactly. We can't do it directly. But how do we do it? Well, again, if you practice polar integration, if not, there should be a refresher. You use double angle. So, in particular, note that cos 2 theta, so no. Right, so cos 2 theta, that's going to be cos squared theta minus sine squared theta. You should remember that. But you can quickly derive that because they give you the double angle in the formula book. So cos A plus B, just set A and B to be theta. Theta add theta is 2 theta, and then you just go from there. But you should remember that by now. Should be quite quick on that. But yeah, so then we can use the Pythagorean identity. Cos squared and sine squared is 1. So get rid of the sine squared to just get cos squared. Cos squared minus 1 minus cos squared theta. And that boils down to 2 cos squared theta minus 1. Oh. And then that would mean cos squared theta, or 2 cos squared theta, I guess, would be cos 2 theta minus 1. But what does that mean? Well, the area, then we can substitute this in then for cos squared. Well, uh, let's bring our integral back. So our area is 200 lots of the integral between 2 pi and 0 of 9. Uh, of 9 plus 12 cos theta, and then plus 4 cos squared. Now 2 cos squared is cos 2 theta minus 1, so if we double it, we get 4 cos squared. So that's going to be plus 2 cos 2 theta minus 2, and that would be d theta. Okay, now we can integrate this. So that's going to be 200 lots of, and then we do the definite integration. So that's going to be 9 theta plus 12 sine theta. Remember your integrals of cos and sine. Cos integrates to the positive side. There's no negative there. Remember that. Plus 12 sine plus sine 2 theta. So again, this integrates to sine 2 theta, but instead of doubling, we halve it. We're dividing by 2 because we're integrating, not differentiating. So 2 over 2 is 1, so just sine 2 theta minus 2 theta between 2 pi and 0. Okay, now we just substitute this in. So that would be 200 lots of. Now 9 theta minus 2 theta, we can simplify that to just 7 theta. So that'd be 7 lots of 2 pi plus 12 sine 2 pi plus sine of 2 theta. So that'd be 4 pi uh, minus. Oh, hang on. Minus. And then another pair of brackets, and then we substitute 0 in. So 7 feet, 7 times 0 is 0, then 0 plus 12 sine 0, plus sine of 2 of 0 as well. 2 zeros is 0. And so we essentially just put that into the calculator. So that's going to be, if we put that into the calculator, we get 200 of 7 pi plus 12 sine 2 pi plus sine of 4 pi minus 12 sine of 0 plus sine of 0. And you get this. So apparently you get 1400 pi. Okay. So that is our area, right? And that would just be units. We don't have a unit for this, so it could be units squared because it's area. Okay. Okay. So that's the area. So then the volume would be, if you remember then, because what the volume of the so how much water goes in, that'd be the volume. So that's surface area. 1400 pi times 90. And we're gonna have to make the unit centimeters squared here because this is in centimeters. Um, so we have to match, right? So centimeters squared. That's gonna be 126,000 pi centimeters cubed because it's in volume. Okay. Hang on, I think I did something here. Hang on. Hang on, I got a number wrong here. I bet I've misread a sign here. 400 lots of 11. Oh, okay. Uh, okay, so it needs to be 11 feet and not 9 feet, not 7 feet. So we need to add 2. Why are we adding 2 then? Hang on. Did I substitute it in wrong? Let's have a look. Cos squared minus sine squared. Well, that's still going to be cos squared minus sine squared is 1 minus cos squared. Yep. So that'd be 2 lots of, yep. Uh, hmm. So that's 9. What is minus, isn't it? Cos squared plus sine squared is 1. So substitute sine squared is 1 minus cos squared. That's what I've done here. Uh, I've done something really silly here. Maybe you can spot it. It'd be an exercise. Cos squared minus 1. So that'd be minus 1 plus cos. That'd be 2 cos. Oh, it's because I'm adding 1. Oh, so how did I? Ah, cos 2 theta plus 1. Oh my lord. Why did I do that? You add 1, yes, because you're just rearranging the cot. Why did I not do that? So that'd be plus 2, and then that'd be plus 2 theta. So that'd be 11 knots of 2 pi. So therefore, new answer. So 11 pi, not 7. Okay, let's put that in the calculator again. My God. There we go. See, this is good. Okay, so this is good. You know what I mean? This is good practice for so you can see the common pitfalls. So don't make the mistake I did there. So then that's sine of 4 pi. God. Okay, there we go. There we go. 4400. There we go. And that's what the mark scheme got. Cool. Finally, so then the volume then, putting the right area in, is 4400 pi times 90, and that will be, oh, this big number here. Okay. That would be equal to 1244070.691, and that'd be centimeters cubed again. Okay. There we are. So then that's the volume. So let's have a look then. What's it saying? So that's the volume, the capacity in the pool. So then it says water flows through a hose pipe at a rate of 50 liters per minute. Given that the pond is empty, so how long will it take to fill completely? Okay, so we need to then convert centimeters to, so then the rate, obviously, so how much minutes, I guess, not the rate, sorry, minutes taken. But we know it takes 1 minute for 50 litres. So then how much volume there is in total. We need to convert this to litres. Now, actually, you do need to just know, I don't think there's a way of learning this, but 1 litre is 1,000 centimetres cubed. So that means this has to be 1244070. Hang on. Let's write that meter. That's going to be out over 50 because it's 50 litres per minute. That's going to be 1244070.691. That's in centimetres cubed. To get it to litres, we're going to divide by 1,000. Okay. And so the minutes taken, if we put that into the calculator, so divide by 1,000 and then divide by 50, you get exactly 723 over 25 pi, which is 24.88 mins. So does it say to the nearest minute? Let's have a check. Give the answer to the nearest minute. So yes, we're going to round up. So 25 mins to nearest min. Okay. And that's your answer. I do think it's quite harsh to make you to expect you to know liters to centimeters cubed. If you don't know, essentially the way liters is made is by forming a cube with side 10 centimeters, 10 cm, 10 cm. So obviously we know that a cube of 1 by 1 by 1 centimeters the volume is going to be 1 centimeter cubed. Similarly, how you form a litre is by timesing this together to get 1,000 centimeters square cubed, and this is defined to be a litre, right? So 1 litre is instead of 1 centimeters by centimeter, it's 10. So then you get this equivalent, you get this conversion rate, yeah. But I don't know. I think they should have told you that in the question. 1 litre should be equal to about, but apparently they expect you to know that. But yeah, that's how litres work. But yeah, hopefully that's yeah, I like that question. It really assesses your knowledge on tangents, so dx d theta 0 and that business, and it assesses your polar integration, which are two key. They could ask both, like this question, or they could ask for one or the other. But this question practices both of those skills. So hopefully that makes sense. So again, to run down for this part, we need to essentially find the volume of a pond which has this surface with a depth of 90. So the surface area times the depth will give us the volume. And then simply to work out the surface, this is the area, this is the curve. So we need to use integration to find the area of the curve, which follows this suit, right? It follows this method. So it's like any other pilot integration question, and then some stuff at the end. Okay, hopefully that made sense. And then obviously part D, silly little limitation question, typical with modelling. So you could just say stuff like, oh, well, the pond will not exactly be the shape of the polar curve. So the actual pond shape will not be exactly the shape of the polar curve of the curve, right? Something like that, right? It's not exactly like the model's idealistic, but there are like I don't know. It will not be perfectly that shape, right? It's not going to be exactly symmetrical. Say around obviously the initial line, right? It's not going to be symmetrical. There's like realistically there'll be some differences here and there. Something like that. You just got to put something like that down. Then we're on question 4 now. Hopefully it made sense. Again, let me check for comments. Okay, I think we're good. Cool. So that's polar. Again, I really would look over this question because I do think there will be quite a hefty polar question on there. I love this question because it assesses everything to do with polar. Tangents, sketching even, and uh, areas, and even some modelling as well. So it has it all. Okay, now I'm proof by induction. Now, this is to do with recurrence relations. Now, in the textbook, I'm aware it's divisibility, series, and matrices, but the spec technically said you can apply it to anything, really. And the example they like to give is recurrence relations. I believe this came up with one of the specimen papers. But they've not asked it since. But they did ask a while recently into proof and deduction related to differentiation. So they do like they will. You never know. They might throw it in a different context to what you expect, and this will be one of them. Yesterday I did a divisibility proof. Personally, I think divisibility will come up, but this is good practice as well. If this comes up as well, so hopefully this will give you practice. So, proving a recurrence relation. So what's happening here is typical recurrence relation. You should see this in sequences and series in normal maths. We need the two previous terms to get the next term, which isn't ideal because say if we wanted to find 100th term, we'll need to find the 99th and the 98th, and then to get the 99th and the 98th, you need to keep going back to get the 97th, the 96th, the 95th. So really, you need to keep going all the way back to U1 and U2. That is rubbish, right? To predict any sort of higher term in the sequence, it's rubbish. But what this usually gives us a direct way for any n to substitute and get the un directly, right? So we don't need to find previous terms. We don't need to do any backtracking. We can just directly substitute n in. And we need to prove that this holds, and we prove this by induction. Okay, so that's the whole idea. Hang on. So let's write this out. So what's it? U1 equals something. 1. U2 equals 5 UN plus 1, or UN plus 2, sorry. UN plus 2, 5 UN plus 1, minus 6 UN. And U2 was, what was it? 5. Okay, and we need to prove, so our aim is to show or prove that UN is directly 3 to the n minus 2 to the n. Okay, so like with anything, you're going to need a basis. Now this is a bit different because obviously it starts from n is 1. Okay, so again we know U1 is 1, so U1 by the formula it's 3 to the 1 minus 2 to the 1, which is 1, which is true because obviously it's given U1 is 1. But we need two values. You'll see why we need two values in a minute, but that's because there's two terms we need to work out the next term, right? We need the term before and the term before that. So n equals 2, then u2, and you'll see why in a minute. U2 is 3 squared minus 2 squared. That's 9 minus 4, which is 5, which is also true, right? If you look at the initial condition we were given is 5. So therefore, statement is true for n equals 1 and n is 2. Now our assumption, so this is where it's going to kick in. Oh god. So normally, with a normal induction, if you were to then just say n is k, as usual, obviously you say what, u to the k is 3 to the k minus 2 to the k. That's fine, but then say then you said for the induction uk plus 1, you would get 5 uk. You'd have to use what we're given here, minus 6 u to the k minus 1, right? We need to go 2 times back, but we don't have anything for uk plus 1. So we need actually two numbers to assume true here. We need the first two numbers, n is k and n is k plus 1, because that would then allow us to induct nk plus 2, because then we can use the first two terms into our recurrence relation, which is also why we needed two terms in our basis, because we need to start with two values that are true, and then we work our way up. So it's not 1 because there's two terms we need here. Okay, un plus 1 and un. That's the key distinction with these recurrence relation questions. So nk and nk plus 1. So I'm going to say assume true. Statement is true for some integers n equals k and n is k plus 1. So therefore u to the k would be 3 to the n, 3 to the k, 3 to the k minus 2 to the k, and likewise u to the k plus 1 would be 3 to the k plus 1 minus 2 to the k plus 1. Just using our aim here, because we want to assume this is true, so we use this formula. Now the induction, now this is why we needed these these pairs of values here. Now we're going to let it be the next number. So let n be k plus 2. So now we need to use the recurrence relation we are given and then get to this form here. That's how induction works, right? And this is why we needed two assumptions here, because we're going to need two different numbers here. So yeah, so that means UK plus 2, remember, is 5 UK plus 1 minus 6 UK, right? So hopefully you can see that's true. So that's us using recurrence relation. And what our aim now is, well, we know what UK plus 1 and UK is, don't we? So we substitute that in. So 5 of 3 to the k plus 1 minus 2 to the k plus 1 minus 6, 3 to the k minus 2 to the k. And essentially now we need to make this UK plus 2 look like this. So what's it going to look like? UK plus 2 is going to look like 3 to the 2k plus 2. No, k plus 2, sorry. Minus 2 to the k plus 2. That is our aim. That's what we need UK plus 2 to look like, okay? So that's what we're going to do. So we're going to need to just manipulate some indices here. So I think it's best, perhaps, to get everything in terms of 3 to the k, okay? Or 2 to the k, because then we can compare them. So that's going to be 5 lots of 3, lots of 3 to the k. So we can bring a 3 out and a 2 out. Minus 6, 3 to the k, minus 2 to the k. And that's going to be 15, lots of 3 to the k, minus 10, 5 times 2, lots of 2 to the k, minus 6, lots of 3 to the k, plus 6, let's write it here, plus 6, lots of 2 to the k. Okay, hopefully you can see we've done now, we just substituted and using index laws. Now we have 15 lots of 3 to the k minus 6 lots of 3 to the k, so that's going to be 9 lots of 3 to the k. And hopefully you're going to start to see why this is good news. 9 is a multiple of 3, that will help. And likewise, minus 10 lots of 2 to the k plus 6 lots of 2 to the k. That is going to be minus 4 lots of 2 to the k. Again, a multiple 2. Well, that's what we're going to capitalise on. Let's write this in terms of 3. That's going to be 3 squared, 3 to the k, minus 2 squared, 2 to the k. And this is going to be that. If we're timed, so remember now, if we are timesing a to the n times a to the n, if we have the same base, a, 3, and we times in two different powers, we add them together, right? That's our index law. So 3 squared times 3 to the k is simply 3k plus 2. And likewise, with this, minus 2, 2 add to k, that's going to be k plus 2. Is this not there on the exact form we need it in? Yes, it is. So we've done it. So therefore, good news, statement is true for n is k plus 2. And actually, I like this question as well because it's kind of reminiscent to divisibility proofs, because all that is about manipulating indexes as well. So this is good practice as well for an divisibility question, because the bulk of it is essentially also manipulating indexes. Okay, but that's how this works. So again, the statement is the same. So therefore, since statement is true for n is 1 and n is 2, and is also true for any given number n is k plus 2, provided our assumption is true, so provided uh, it is true for n is k and n is k plus 1. Therefore, the statement has to be true for any integer n. N greater than 1. Cool, so that's that then. So yeah, it's a very similar mechanism, but obviously recurrence relations, you need two different values here instead of one, like usual. Because, well, if you just, even if we tried to use one, well, then you're going to say, for example, U2 would be 5U1 minus 6U0, but we don't have a U0. So we're going to need to consider two numbers, right? So even if you kind of forget it, if say this comes up, right, say if you only choose one, it will break down. So then hopefully you should realise, well, let's try two numbers instead. After that, it follows the exact same method, right? Yeah, so that's recurrence relations. That's yeah, they could also perhaps ask you for one term recurrence relation. So say if you n plus 1 is say like 7 lots of un add 5 or something like that. Then you only just need one number because obviously one number to assume. So you could just assume n is k and then induct with k plus 1. That'd be completely fine because you only need one previous number, right? But whereas here, our example here, you need two previous numbers. So you're going to need to consider two assumption values before you induct, okay? Okay, hopefully that's clear. So that's induction. I think that's a good little example to try our knowledge on. Hopefully that's clear. But yeah, I'm going to move on to the next one. Okay, we've got roots of polynomials. So we're given a cubic equation 4x cubed plus px minus 4. Let me zoom in actually. 4x cubed plus px squared minus 14x plus q is 0. And we're given some information about the roots. So it's the roots of polynomials. We need to show that p is 12. Okay, let me write the cubic then. So that's going to be 4x cubed plus px squared minus 14x plus q equals 0. And we are given that when the roots are alpha, beta, gamma, that alpha squared plus beta squared plus gamma squared is, what was it? It was 16. And we need to show that p is 12. Okay. Well, this is roots of polynomials, so you're going to need to look at the coefficients, right? So you're going to know that the only information we can work with, really, with regards to the polynomial is that this represents the pair sums, right? So remember it goes minus b over a is the sums, so just a, which is alpha plus beta plus gamma. Then you have c over a, which is the pairwise sums, alpha beta, which will be alpha beta plus alpha gamma plus beta gamma. And then you're going to have minus d over a, which is sum of alpha beta gamma, which is, well, it's just literally alpha beta gamma, right? Okay, but so c over a, so obviously polynomial a, b, c, and d coefficients. This is going to be the pairwise, right? So minus 14 over 4, which is 7 over 2, and that's going to be alpha beta plus alpha gamma plus beta gamma. Okay, again, nothing you can do there. There's too many variables here to solve, to do anything with. But we're also given this fact here, and actually another thing you should know from the topic is we can consider brackets. So I think this looks very much that we need to consider alpha plus beta plus gamma squared. I think that looks like this, right? And if we expand that out, that's going to be alpha squared plus alpha beta plus alpha gamma plus alpha beta again plus beta squared plus beta gamma, if we can write gamma, plus alpha gamma plus beta gamma plus gamma squared. If you expand that, right? And actually notice that this, if you rewrite this, and this is a key thing, is to write it in terms of the pairwise sums, the sums, the single sums, the double sums, and the product, right? So I would split this up as alpha squared plus beta squared plus gamma squared. And notice alpha beta is twice, B alpha gamma is twice, and beta gamma is twice. So this is two lots of alpha beta plus alpha gamma plus beta gamma, right? But do we not know expressions for both of these? I think we do. Um, so actually, what this is saying is alpha plus beta plus gamma squared. Well, alpha squared plus beta squared plus gamma squared is 16. We were given that, right? We can substitute that in. Plus two lots of, and we know what the pairwise sum is. That is 7 and minus 7 over 2. That's two lots of minus 7 over 2. And therefore that will boil down to 9. So actually that means alpha plus beta plus gamma is just 3. Okay. Uh, or do we need to consider minus 3? They could sum to the positive constants. Okay. Okay, so I don't think there's a way that we know that the roots are all positive. So if we're squaring in this case, it has to be plus or minus 3. But hopefully that won't matter. Okay, so with that in mind, well, actually, isn't the sum minus b over a? So minus b over a is actually minus p over a. So minus p over 4. Uh, so about also reminding that a, b, c, and d correspond to the coefficients on the polynomial. So minus p over 4. Well, that's going to be the sum, right? So it's going to be alpha plus beta plus gamma, which is plus or minus 3. So we need to consider them separately. So either minus p is, well, minus p over, okay, so minus p would be positive 12. Therefore, p is minus 12. Or minus p would be minus 12. So we times in 4 across, right, to get rid of the fraction. Solve for p, that means p is 12. But are we not told that p is a positive constant? So, yeah, the real positive constant. So, the only solution here, therefore, p is 12. And that's part A, right? And what this also means as a result is alpha plus beta plus gamma, for this to be true, alpha plus beta plus gamma has to be positive 3, right? Because then 3 times 4 gets us 12. Oh, no, no, minus 3, sorry. The right-hand side scenario. So 4, times by minus 3 gets us minus 12. So minus p to minus 12. So this happens when alpha plus beta plus gamma is minus 3. And this happens obviously when the sum is positive. So that has to be minus 3, okay? If that helps. Okay, so that's part A. So then part B, Now we know that. I mean, we're given this further one, some of the reciprocals. Determine Q. Well, again, so the key with this is again, try and manipulate it in terms of uh, the sum of the roots, the product, and the products, right? Sum of the products. So we have 1 over alpha plus 1 over beta plus 1 over gamma. Let's simplify this. So that's going to be beta gamma. If you have a common fraction, common denominator, sorry. So times by beta gamma here, then times by alpha gamma, uh, then times by alpha beta, and that'd be all over alpha beta gamma, and that is equal to what did it tell us? 14 over 3. Okay. Okay, but we already know what the pairwise sum is, don't we? The pairwise sum is minus 7 over 2, right? We did that in part A. So therefore, minus 7 over 2 over alpha beta gamma is 14 over 3. So then that means that 14 alpha beta gamma is going to be 3 lots of minus 7 over 2 by cross multiplying. And therefore, alpha beta gamma, if we solve that, would be 3 minus 7, 3 minus 7 over 2 divided by 14 would be minus 3 over 4. Okay. Um, so then that means okay. So that means well, the product. So let's have a look at our remember our polynomial here. The product alpha beta gamma has to be minus d over a. Well, d is q, the constant, right? So therefore minus q over 4, which is a. So minus q over 4 has to be equal to 3 over 4. Minus 3 over 4, sorry. So then if we solve across, well, get rid of the minus. We can get rid of it. So 4q has to be 12, right? 3 times 4. Therefore, q is 3. Okay, good stuff. Let me check I've done that right so far. What's the paper? June 2022. Okay, I'll leave it there for now. And then let's have a look at part C. So, we are then told, without solving the cubic equation, which basically means use roots of polynomials again, so use the facts we know, that we need to find this product here, alpha minus 1, beta minus 1, and gamma minus 1, right? So, yeah, again, I think the best way to approach this is to realise what this is. So when you got something like that, it's best to try and expand it and see what you can do with it in terms of the products and the sums. Right here, it's not directly clear because alpha minus 1, beta gamma. It's not much we can do here. We could. I guess one way you could do it is doing a shift, because we know P and Q now. You can shift the roots by saying W is x minus 1, and then this would correspond to the product of new roots. I might do that actually. And then obviously the product would be minus d over a of the new uh, cubic. Or let's see what happens if we expand. Maybe we can work with it. So that'd be alpha beta, which is a good sign. Minus alpha minus beta plus 1 times by gamma minus 1. Then that'd be alpha beta gamma minus alpha beta minus alpha gamma. Uh, 1, 2, 3. Plus alpha minus beta gamma plus beta plus gamma minus 1. And actually, that's great because we know all these three, don't we? We've already worked all these out. The products, the pairwise sum, and the single sum. So let's rewrite this. So alpha beta gamma minus alpha beta plus alpha gamma plus beta gamma, and that's gamma by the way. um, Plus alpha plus beta plus gamma minus 1. But we know all three of these, don't we, in terms of the roots of polynomials, right? The coefficients. Well, alpha, beta, gamma, we worked out here, actually. Here, alpha, beta, gamma is minus 3 over 4. So that's going to be minus 3 over 4 minus the pairwise sum. Did we work that out? Yes, the pairwise sum here is minus 7 over 2. And the sum is minus 3, right? Uh, Here, right? Alpha plus gamma has to be minus 3. Then minus 1, put that into the calculator. You get minus 5 over 4. So that is the value of that expression there. Okay, let me check this. I think I got the wrong paper down for this. I don't think it's this particular paper. I can't find it anywhere. Oh, here we are. Minus 5 over 4 is the answer. Okay, cool. Uh, So that's all right. Okay, so that's all right. I've not told you anything. Lies. Okay. The other way we could do it, I'll do it here actually. You could notice, but it doesn't always work out like this because I think the best way to approach something like this, when you know the roots of polynomials, how it relates to the cubic, you're gonna need to, like part B, you're gonna need to manipulate like I said, the sum, the pairwise sum and the product, right? Like we just did, right? Um, but alternatively, and I guess this would be a revision for transforming a cubic, right? W is x minus 1, and then this new root here by this coding will have these roots, right? Alpha minus 1, and then you could do minus d over a. So let's have a look how that would work. So that'd be 4 lots of. Does the Mux team do this? So essentially, we're saying w is x minus 1. So then x would be w plus 1. So 4 of cubed plus. Now p was 12. plus q, which was 3, wasn't it? And that equals 0. So then w plus 1, w plus 1, w plus 1, that's equal to w squared plus 2w plus 1, w plus 1, that'd be equal to w cubed plus w squared plus 2w squared plus 2w plus w plus 1, which simplifies to w cubed plus 3w squared plus 3w plus 1. So then 4 lots of that would be 4w cubed plus 12w squared plus 12, oh, 12w plus 4 plus 12w squared, that'd be 12w squared, 24w plus 1 minus 14w minus 14 plus 3 equals 0. Then simplify that, 4w cubed, 12w squared are 24w squared, 12w, 24, 36w, minus 36 minus 14 would be 22. Plus 4 plus what? 5. 5 and 3. 8. 8 minus 14 would be minus 6. Okay, and then therefore the new product would be minus d over a, which should be 6 over 4. Oh, hang on. Oh, hang on. That gets 3 over 2. That's not the right answer. Hang on. 4w cubed. 4 times 3 is 12. 4 times 3 12 plus 4 plus 12w squared plus 24w. Oh, that's why. Plus 24w plus 12 there. Not 1, 12. I don't know why I didn't write a 2 there. What? Oh my god. Minus 14w minus 40. Okay. There we are. So the new quadratic would be, the constant would be now 4 add 12, which would be 16, minus 40 would be 2 plus 3 is 5. So that'd be minus plus 5. So the minus d over a would be minus 5 over 4, which is what we got before, didn't we? If you look here, that was part C. Oh, hang on. That was here, right? We worked this out alternatively using expanding it directly and using our knowledge of the roots of polynomials. But there are two ways of doing that. But I think you can't always apply a shift, like this. But you can do it that way, and this is good practice. If they ask you to transform a cubic, right? This is the method. So obviously alpha would be x. So really, remember the only values of x here that solve this is alpha, beta, and gamma. So x would be alpha, beta, or gamma. So then really, when you apply the shift here, if the roots are alpha minus 1, that means w have to be x minus 1, right, in place of alpha, beta, and gamma. That's the way we can transform it, right? So just notice that really alpha and beta gamma is in place of x. So therefore, that's the transformation, right? I think people get bit confused about what substitution to use, but it really isn't that bad. Hopefully, that's a roots polynomials refreshment. Now we're on this question. So I did cut up the earlier part because this is part C, but it was just asking for inverting a matrix and when and stuff about when it's consistent. That should be fairly fine, and I don't think they'll ask that. However, this part of the question was quite interesting, which is why I have it here. So it's asking them again about vector equations of intersection, like I did in the earlier part. I really do reckon they will ask something like this in your paper tomorrow, which is why I'm going over it again, because I did a very similar question yesterday. And actually, it combines vectors with systems of equations, so the examiners might like to answer that, ask that, sorry. Anyway, so question 5. So that's where I have a read. So the value of q. So the following planes intersect in a straight line, and then determine the vector equation of the line. So let's write this down. So we're going to have 4x plus 5y plus 7z is 1. Like what's it? X plus y plus. What was the other question? The other equation? X plus y plus z is q, and what was it? 2x plus y minus z is 2. Okay, so then it's asking what value of q makes there essentially there are infinitely many solutions, right? So the wording was uh, the planes intersect in a straight line. So obviously a line has infinitely many points. So there are infinitely many solutions to this equation here. Um, Well, the strategy for this is essentially to show that two equations are basically equivalent. That's the strategy here. So they can solve them, but they're equivalent. So essentially, you have two pieces of information with three unknowns. Well, you can't solve it uniquely, can you? So the only way is so it's kind of like saying 2x plus 3y plus z is like 2, and then x plus 3, I don't know, 4y minus 2z is like 7. So two different equations, but there's three unknowns. So actually, what happens if you try to solve it for substitution, you'll have x is something, I don't know, x is x. Y would be in terms of x, so it could be like 2x plus 6, and then Z will also be in terms of x, 3x plus 8 or something. I don't know, that's not the solution. I'm just saying that's what you could get out of this. But the idea is it's no one unique solution here because you can pick any value of x and it will satisfy both of them. So that's essentially what we need to do is essentially to boil this down. That's the whole idea is to show that two equations are essentially equivalent. So then it forces us to have infinite solutions. So there's a general method to this, right? And they have asked this a few times before. So this is how you approach the question like this to show there are infinite solutions. Now, do not use the determinant because if the determinant of this matrix here of like 4, 5, 7, 1, 1, 1, 2, 1 minus 1, if it's set to 0, that does not immediately mean there is what's it called? Uh Infinite solutions. It can be infinite solutions or no solutions. So that's not a good way of doing it. And actually, the value of q doesn't. Well, I mean, uh, never mind with that. But essentially, that's not. We can do better than that, is what I'm saying. The determinant is only good, by the way, for showing that there is a unique solution. So if it's non-zero, so it's not equal to 0, then there is a unique solution. But it's not good for proving there exists infinite or no solutions, right? So we need to come up with a way of showing that there are two equations are equivalent. Okay, I'm going to stop waffling, so let's go into it. So the idea is to eliminate, if I label this 1, 2, and 3, equations 1, 2, and 3, the idea is to eliminate a variable, and I think the best way is to not eliminate z, because if I simply add 2 and 3 with no more faffing around, that gets rid of z. So that would be 2 and 3 would give 3x, so 2x add x. Y add y, we get 2y, and that would be q plus 2. Okay, now I need to eliminate z from 1. So there's two ways I can do that. I can either substitute z equals directly into both of them to just get x and y, or I could again do like what's it called? I could subtract. So notice that this is 7z in equation 1, and this is z. So I think if I times by 7, so 7 times equation 2, that would be 7x plus 7y plus 7z is 7q. And then if I think I'd call that 4, and then I subtract 4 from equation 1, well, then that's 7x minus 4x, which is 3x. 7y minus 5y is 2y. And 7z minus 7z is 0. And that's going to be equal to 7q minus 1. And actually, notice here, we reduced it to two equations, but they're identical. 3x plus 2, wow, they should be. But notice the left-hand side is exactly the same, and that's good. If they are infinite solutions, that has to be true. Well, if there are infinite, okay, it has to be true, but two possibilities are happening here. So, either there are no, like we discussed, there are now either no solutions, or there are infinite solutions, because there's no unique solution here, because they're the same equation. We would have enough info to solve it uniquely. So it's either infinitely many or no solutions. Now, two possibilities can happen. Either they are different or the same, right? So say that's equal to 1, and then the second equation was minus 5. That cannot be true, right? So therefore, there are no solutions here. Or they have to be the same, and that will give us infinite solutions. So say if we had 4 and 4, that would then mean there are infinite solutions, because like I said at the start, they are equivalent, right? You have two equations that are equivalent, so that means infinite solutions arise. But how do we make sure then that the two equations are identical? Well, the left-hand side is the same on both of them, but the right-hand side has to be the same as well. But that's in terms of, so that would mean q plus 2 has to be equal to 7q minus 1 for them to be the same, to be equivalent, right? So now we solve for q. So then q plus 2, 7q. So let's subtract q. So 6q would be 3. That means q would be a half. And the q has to be a half then to ensure there are infinite solutions, because that means that we have equivalent what's it called? Equivalent equations, right? It doesn't seem clear at first that they are two are equivalent, but we can make them equivalent, okay? And the strategy is to eliminate a variable to make that more clear, okay? So, the idea is essentially to get use one equation to get rid of z on the other two, to get two equations without the variable z. Okay, so all x or y, but this is the general methodology for showing three equations have infinite solutions. Okay, you need to. This is the method, right? Hopefully that is clear. Hopefully. And then the other question is to find a vector equation for the line of intersection. So as they said, for this value of q, there are infinite solutions, meaning that the solution, all three of them intersect in the line. Okay. So we need to find this vector form. So obviously, every vector has to be in this form. So there's a point that we know on the line, and there's a direction vector. Okay. Well, there are two ways of doing this. Well, we have all three equations. So, I think we can just find 2 points and then we know a point and a direction vector, because the direction vector is you can just take the difference of 2 points, right? So let's find 2 points. And to do that well, you can just say x is 0, because on the line, obviously it'd be x, y, z essentially. It would have to pass through the whole. Obviously, that's how lines work. Think about it in 2D. A line has to pass through the entire x. Has to have an x coordinate for every right. How do I say this? There will be x coordinate at any lot on any of the x-axis, right? So there won't be any missing values for x here. So say so x has to be 0, but we don't know the corresponding y or z value. But that's fine as long as we set one variable to be 0, we can find the missing. But I didn't say that very well. But essentially, okay, let's try it again. Because it's a line, right? That that goes through the whole axis, right? It goes from negative infinity for x to positive infinity. It contains a whole real line of x values. So for any x value, will have a corresponding y value. Is what I'm saying here essentially. Every x value will have a corresponding y and z value on the line. Likewise with any y value, it will have any x and z. So essentially, if we just plug in one particular value of x, y, or z, we can find the missing values that'll be on the line. And we can use these equations here to find that. So let's go over that. So x is 0. Hopefully that explanation is clear. So that's the strategy here. X is 0. Let me just substitute x is 0 to any two equations. So saying 2. So 2 becomes y plus z is q, which was a half, and y minus z is 2. We can add them together, say, so then 2y is 5 over 2. 2 plus a half would be 2.5, yeah, 5 over 2. Therefore, y would be 5 over 4, okay? And therefore, z would be, substitute that in, would be half minus y. So half minus 5 minus over 4, which would be, or equivalently, you probably could put this in the simultaneous equation solver in your calculator. But anyway, doing that would get minus 3 over 4. So 1 point is P1, 1 point on the line would be 0, 5 over 4, and minus 3 over 4. And then point 2, well, another point. Well, now let's instead let y 0, for instance, right? You don't have to be 0, just make it be any value. Obviously, 0 is the most simplest to work with, right? Again, don't try x like 1,070,000. You don't need to do that, okay? Just keep it simple. So then y 0, then again, equation 2 boils down to x plus z is q, which is a half, and then equation 3 would be, oh, there we go, 3 would be 2x minus z is 2. And then solve that again, so you can add them to get 3x would be 5 over 2. Therefore, x would be 5 over 6. And then therefore z would be half minus x. Half minus 5 over 6 would be minus a third. So therefore P2 would be, well, x is 5 over 6, y was 0, and z is minus a third. Okay, and because there are infinite solutions, by the way, you might think, oh, what about if we need to check it's consistent with with equation 1? But because of how we define q, there are infinite solutions. It will have for any if we pick values x and y and z in this case, that solves 2 and 3. It will automatically solve 1 as well, because that's the idea of infinite solutions, right? We don't need to check for consistency in that manner. Okay. purely because of how we define Q. So, yes. Hang on, I got the charger in. So now we know 2 points. Well, the direction vector is simply the difference, right? So difference of any of them. So difference of 2 minus 1, 5060 minus the third, minus 0, 5 over 4 minus 3 over 2. 5 over 4 minus 3 over 4, sorry. And that would be 5 over 6 minus 5 over 4 and minus a third plus 3 over 4 would get you 5 over 12. And then therefore the vector line would be 0, 5 over 4 minus 3 over 4. Just pick point 1, for instance, on a point we know on the line. Add lambda lots of 5 over 6 minus 5 over 4 and 5 over 12. Cool. Now there is an alternative method that I really do want to go over. I think this will help a lot for questions even outside of this example. Let me check that's right first of all. It should be, but no, 2020 paper 2. Um, uh, yeah, that's fine. That's cool. Okay, that's a method. But the other method is to consider the cross product. So I'll explain what that is. I did it in the last stream. Um, but there was a very similar question to this last stream, but you can't use it using this method because it didn't give you the equations of the plane, but you still needed to find the vector of line of intersection. That's where this method comes in, and it's more has more use, right? And that's the cross product. So instead, let's have a look at geometrically. Well, these are three planes, right? Three plane equations, and essentially, this line is contained in or L, the line L, which is contained in all three planes, right? Uh, because it's a line of intersection on all three planes. Okay, so that's for example what that would look like. Now, what that means is that the direction vector L, because it has to be because it's contained in the plane, it's parallel to the plane. What that also means is that it's going to be perpendicular to the normal because it's parallel to the plane, it has to be perpendicular to the normal vectors of the plane. Okay, so normal 1, normal 2, and then normal 3. So it's perpendicular to all three planes. So if we find a vector that is actually perpendicular to these planes, to the normal perpendicular to the normal vectors, we have the direction vector. So the direction vector of L has to be perpendicular to all three normals. But we know what the normals are, don't we? For example, we know that normal of plane 1 is 4, 5, 7, right, in Cartesian form. So 4, 5, 7, hopefully you recognise that. And then the normal plane 2 is 1, 1, 1. And the normal plane 3 would be 2, 1, minus 1. Okay, and now actually, the cross product is this, right? It's this 3 by 3 determinant, ijk, and then we plug in two vectors, right, like this. So the first vector would be 4, 5, 7, corresponding to the ijk unit. And then the second one would be 1, 1, 1. So we put two vectors in, and what this gets us is these two are vectors. This outputs another vector that is perpendicular to both vectors. which is great because that has to be the direction vector, right? Because we said the direction vector has to be perpendicular to all the normals, right? So if it's perpendicular to normal 1 and normal 2, that's what this vector, that's what this cross product generates, okay? And the cross product is in further pure 1, but it's easily learnable and it's so useful for vectors. It really is. And you don't actually have to learn that cross product as well because it is also given in the formula book right here. This vector product here, a times b, so a and b. So this will give a vector that is perpendicular to both a and b. So if you want to find a vector that's perpendicular to two vectors, this is the way to go, and that will become very useful for lots of problems in vectors. So let's work this out. So you should know how to do 3 by 3 determinant. That'd be I lots of 5 1 7 1 minus j lots of 4 1 7 1 plus k lots of 4 1 5 1. So that'd be very quickly 5 minus 7, that'd be minus 2i. 4 minus 7, that'd be minus 3. But it's minus 3, minus j, so that'd be plus 3j. So minus 3 will become positive. And 4 minus 5 would be minus k. So our vector would be minus 2, 3, minus 1, ijk. And that is our direction vector, right? That'll be parallel to the planes or perpendicular to the planes, right? To n1 and n2. Now it will automatically also be perpendicular to the plane 3. Again, because of how we constructed these equations to be infinite solutions because of our value of q. So if we construct a line, like the direction vectors are parallel to two normal vectors, it will automatically also be perpendicular to the third one. So you can pick any two vectors here. Then you compute this cross product, which is in the formula book. That's just working out 2 by 2 determinants. You know how to do that for matrices, right? So then substitute that in, and then you get a vector that's perpendicular to both, which is our direction vector. Hopefully that's clear, right? That's the geometry behind it. And therefore, our equation would then be p plus lambda lots of minus 2, 3, minus 1. And again, we could just pick a point. So again, then to find a point, you use the same method. So you just say x is 0, for example, and then you get the point 0, 5 over 4, minus 3 over 4, okay? Plus lambda of minus 2, 3, minus 1. So that's an alternative way to do it. Just to show, by the way, these are equivalent because 5 over 6 minus 5 over 4, 5 over 12. You can factor 5 over 12 out, and that would be 1, minus 5 over 12 out, sorry. So then that would be minus 1, minus 1, 3, and minus 2. And that's the same, right? Direction vectors, you can take scalar multiples out and it'd still be the same. You just care about the actual direction itself, right? So you can take any scalars out and they're equivalent. So that's the other way to do it. And I like that because I don't, for certain vector problems where you need to find a perpendicular vector to two vectors, there's not a clear-cut method. So the best way to do it for all those problems is a cross product, which is a very, very handy tool. So I just wanted to go over that, and I did in the last stream as well. And like I said, in the last stream, there was a very similar problem, but you could not just find 2 points. Because they didn't give you equations of the plane, but they gave you the vectors, the normal vectors though. So then if you found the normal vectors, then you could just find the perpendicular one using the cross product. So I think this method is nice, but that's the other way to do it, right? But that's that question dealt with. So hopefully, but that's the way to find out a vector for an intersection of three planes. Okay, so that's that question dealt with. And now we've got another vector question. Like I said, vectors will come up. So now we've got this. So two birds. So basically, it's giving us the vector equation of two birds, essentially. And so their flight path, the angle is 120 between them. Find the value of A. Okay, well, this essentially is just saying, it's just using the what's it called? This formula here. So cos theta is the dot product of two direction vectors, d1 dot d2 over the modulus of d1 d2. Okay. Uh, cool. So that's what we've got to do. So the direction vector of the first bird is this part here. So it's going to be 2a0. And d2 is for the second bird. That's going to be 0, 1, minus 1, right? Just reading off the equation of a line. Okay. Did I copy that right? Let's have a look. Yes, I did. So now essentially just substitute that into the formula and then find A. Okay. Well, we're given the angles 120. So cos 120 is going to be 2a0 dot 1, 0, 1 minus 1. And that's going to be over the modulus. So that's going to be the square root of the sum. The square root of the sum of the squares of the components, right? So that would be 2 squared plus a squared times by the square of 1 squared plus minus 1 squared. And so then cos 120 is in degrees, by the way. That's going to be minus a half. And then that's going to be equal to the dot product 2 times 0, a, just a, right? 2 plus 2 times 0 is 0, a times 1 is 1, 0 times minus 1 is 0. Okay. So that'd be a over, that's going to be root 4 plus a squared times by root 2. Okay, 1 squared. Okay, cool. Let's get rid of the root 2. So times by root 2 on this side minus root 2 over 2 is going to be a over root 4 plus a squared. Um, then we can compare. So we could say minus root 2 root 4 plus a squared. It's going to be 2a. And I guess we can bring it inside because they're both surds. We could say that's 2 lots of 4 plus a squared is 2a. Then therefore, if we square both sides, we get 4a squared equals 2. 2 lot, we can expand this out. 8 plus 2a squared, right? So therefore, 2a squared is 8. So then a is plus or minus 2, right? A squared would be 4, so then a would be plus or minus 2. But we've got two solutions here. Have they told us anything? A is a constant. Okay. Well, what we did here essentially was introduce an extra root by squaring. So we need to check them separately. So we need to check a is 2. And so how to do that is to substitute it into our angle formula again. So cos theta would then be what was it? It was this result here, a over 4 plus a squared, 2 over root 4 plus a squared. That's going to be 4 plus 4 plus 4, right? A squared would be 2, so that'd be root 8 root 2. That'd be root 16, which should be 4. So let me simplify that. So that'd be root 16. No, sorry, root 8 So what I'm doing here is substituting A into here to then check, because there's what we call an extraneous solution, because we squared both sides here, we added an extra solution, so we need to get rid of one. So to check, this needs to be equal to minus a half if we sub A in. So that's going to be 2 over 8. 4 plus A squared again would be 4 plus 4, which should be root 8 root 2. And actually, root 2, there we are. That would actually be 2 over root 16, which should be 2 over 4, which should be a half. But that is not equal, that's not minus a half here. We need minus a half. So A2 is not the solution. So A is not equal to 2. So then we check, and this should be right, A minus 2. So therefore, cos theta would have to be minus 2 root 8 root 16 root 2, which should be minus a half, right? And that's great. So therefore, A minus 2 is the solution. Okay. So then part B. Verify that according to the model there is a common point on the flight's path and find the coordinates of this point. Well, that's just equating them together, right? So when we know that R1 is given to be minus 152 plus lambda lots of, what was it? 2A0. And then R2 would be, hang on, no, I need to check the page. R2 would be 4 minus 1, 3. Plus mu lots of 0 minus 1, 1. Was that right? Cool, yeah. So now we just equate them together, right? And essentially, if they intersect, there will be a consistent unique solution. So what do we mean by that? Well, we can combine them together. So R1, firstly, we can express this as minus 1 plus 2 lambda, 5 plus 9 lambda, and 2. And R2 would be 4 minus 1 minus mu, 3 plus mu. And so then we equate them together. R1 equals R2, which means that minus 1 plus 2 lambda equals 4. 5 plus 9 lambda would be minus 1 minus mu. And 2 would be equal to 3 plus mu. Okay, again, you can label this 1, 2, and 3 if you wish. So yeah, so they intersect, we'll get a unique solution for lambda and mu, which will be correct for all three equations, right? So then solve them 1, let's have a look. Well, we can solve for lambda, can't we? So lambda, so lambda would be, well, 2 lambda, I guess, would be 4 plus 1, so that'd be 5. Therefore, lambda, according to this, would be 5 over 2. Then we'll look at equation 3. So we are mu would be minus 1. And then sub lambda and mu into 2. And if there, and obviously you can get a solution for lambda and mu using 2 equations, but we need to make sure the third equation is also correct for these values. If it is correct, then they do intersect, okay, if they're consistent. So let's try that. So it's going to be 5 plus 9 of 5 over 2 equals minus 1 minus minus 1. Let's check that. 5 plus 9, 5 over 2 gets us, oh, Oh, what have we gone wrong here? Oh, did I copy the? I did copy it right, didn't I? Hang on. I don't get the right solution. Why is that? Well, I must have copied something down wrong again. Hang on. Uh, oh, that's why. This was 5 plus. Oh, this was 5 plus a lambda. That's this. That's what I misread it as 9. That's why. But we know a is minus 2, so let's substitute minus 2 in. That's why. Oh, my handwriting. Oh God. I do apologise if other people thought that was 9. That's meant to be an a. There we go. 5 minus 2 lambda. There we go. Now we're back in business. Let's try that again. So 5, and yeah, this leans right now. There we are. 5 minus 2 of lambda, which was 5 over 2. Now that gets us, if we do that right, 0. Yeah, so you get 0 equals minus 1 add 1 is 0. Therefore, equations are consistent. So they do intersect, okay, the birds. But then it asks us to find the point of intersection. But we've done most of the hard work here already. So to find a point, sub, say mu, I don't sub mu or lambda into either equation to find the point. So say sub mu equals minus 1 into R2. So then R2 would equal 4 minus 1 plus 1, which should be mu here. Minus 1 minus mu. And then 3 minus 1. That would be 4, 0, 2. Therefore, point is 402. Okay, that's the point of intersection there. So what we've done is, because we've shown a consistent all three equations when you equate them, so there is an intersection, and the point is when you substitute the parameter in. Hopefully that should be fairly straightforward. And then for part C, it's saying the position of the nest is modelled as being at this common point. The tree containing the nest is in the park. The ground level is modelled by the plane. Determine the distance between the nest and the ground. Well, the ground is a plane, and the nest is a point, and it's the point we worked out in part B. Well, really, we're working out the shortest distance between a plane and a point. So let me reiterate. Let's not reiterate. Restate the point again for part D. Uh, if we can scroll down, that'd be nice. Thank you. Oh my lord, what's going on here? Ah, okay. Part D. That so the point was or the nest is 402, and the plane is, what was the equation? 2x minus 3y. Uh, plus z is equal to 2. So now we need to find the distance, the shortest distance between the point and the plane. Well, actually, it's this formula here, and it's in the formula book. Uh, the distance is this equation here. So the perpendicular distance, which just means minimum, because remember the shortest distance is such that the line is perpendicular, right? So the perpendicular distance of a point alpha, beta, gamma from this equation here, the plane equation, is essentially almost doing the dot product of the vector with the normal vector of the point, right? And we need to add d. Okay, and then um, so the distance, remember, is modulus of 4 times 2 plus 0 times minus 3 plus 2 times 1, and then we need to minus 2 because this is equivalent to saying minus 2 equals 0, which is the form in the formula book, okay? Which is here, right? Plus d equals 0. So d is the value we add on, so it'd be minus 2. And then we need to divide again, similarly, like with the angle, the square root of the length of the direction, the normal vector, right? So that would be the square root of 2 squared plus minus 3 squared plus 1 squared. So put that all to the calculator, you would get 4 2. You would get 8 over root 14. And if you want, you can simplify it, I guess. What does the calculator do? 8 over root 14. That's equal to 4 root 14 over 7 units. Okay, it doesn't actually tell us the units, but that's the distance. Okay, and that's just a simple, yeah, the distance, angle between distance of a point is fairly straightforward. Just use the formula. Just make sure you be aware you need to subtract the d to equal 0 here to use the formula in the formula book, okay? But that's what's going on there. Just a simple application of a formula. Okay, so we're back in business there. So then it says for part D, by considering the model, again, this whole limitation reasoning stuff again that they like to ask there and there. Find a limitation of the model. Well, essentially, um, what's it called? It's saying that essentially these birds are in a straight line path, right? Constantly. And that the angle that when they do cross is 120. I mean, how likely is it that a bird is going to be flying in a linear direction and like air resistance and the wind will not blow them back and forth occasionally, and it'll affect their trajectory, their flight path. I mean, they're not going to fly in the linear straight line fashion, are they? So that's probably going to be a limitation here. Limitation is the birds will not move in a straight line. For various reasons, but that's just not likely. Uh, so I guess with reference to the model, so R1 and R2 will not be accurate paths for the birds, right? So they won't move in the line described by R1 and R2. Okay. Uh, yeah, not reliable as the birds will not fly in a straight line. Yeah, there we go. So that's the sort of thing you need to write. Okay, one question. Was it 6 now? 7? I can't remember. Okay, I want to wrap this up quite soon though. How many questions have we got? Ah, 3 more. Okay, I'm going to rush through these ones then. I'm going to rush. Okay, so Argand diagram. So I'm going to do this here actually. On an Argand diagram, the set of points of this. So don't be put off by the set notation. What this is saying is, well, the z minus 1 plus I is less than or equal to 3. So this defines a circle in the form z minus a is less than or equal to 3. So the centre is a and the radius of 3. So it's going to look like this, right? So the centre is 1i. So 1 plus I here. A radius of 3. So it's going to look like that. And obviously inside the circle, anything that's less than 3 has to be inside. And then the second part is pi over 4 arg of z minus 2 less than equal to 3 pi over 4. By the way, that's real and imaginary. You need to label the axis. It's going to be z. Again, it's kind of like this again. You need to do z minus 2. So again, you kind of got an argument z, but then we need it starts at 2, right? So then we need to measure our argument for z from this point, not from 0, 0, but from 2. So we're shifting it, right, to 2. So then the argument, so remember the argument is essentially the angle it makes. So here, 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 with the positive real axis. So pi over 4 is 45 degrees. So it's going to be kind of there. So midway between 90 and 0. That's pi over 4. And 3 pi over 4 is 135 degrees. So it's between 90 and 80. So it's going to look like that. Okay. So that's going to be this loci here. So this angle here, so any z in this region here will be in this point, okay? Oh god. So then we need to shade on the same Argand. So then we need to factor this in, this circle here. Let me get rid of this here. So that's the argument loci. So then the circle is again 1i. So it's going to be here. And so it's going to look like this. Okay, roughly. And so if it's less than or equal to 3, it's going to be the whole circle. But if it's between pi over 4 and 3 pi over 4 here for z, it's simply going to be this region here, right? That should be your 5 marks there. So quite complicated Argand diagram question, but I picked it to illustrate that type of thing. They might ask you to do that. Don't be put off by the set notation. All this is saying is the possible values for z, which are complex. So obviously we're in the complex domain, so that means nothing. So such that, so that's what the colon means. Z, this loci here, which you should be familiar with, is a circle. And again, all the values of C, the complex numbers, such that this point is true here. So really just try and cut through the waffle here and work out, and this means and as well. So from G to C, you should remember and, or, and obviously the dash for not. Okay, that's for set notation. You know when you did your Venn diagrams, and also for A-level math in the stats section. But anyway, so it means and, so both of them have to be true. So you have to shade both regions, where the region where they both are shaded, right? Which is this. So there you are. So that hopefully that's clear. Speeding through it a little bit quickly now. To part B. So we need complex number satisfies both equal to 3. So this is quite common. So really you just need to say let W be x plus IY, and then it all follows from there, because what we're saying is mod x plus IY minus 1 minus I is equal to 3, which then means if we group that together, x minus 1 plus I of y minus 1 is equal to 3. Therefore, we can square it to say x minus 1 squared plus y minus 1 squared is equal to 9, sorry. And then I'm going to leave it there for now, for here. And then I'm going to look at this other bit here, so the argument one. So again, this is saying arg of x plus iy minus 2 is equal to pi over 4. Otherwise, and then we can again combine it. So x plus, oh no, sorry, x minus 2 plus iy is equal to pi over 4. So that's the y component, the I, and the real component. So again, you should know that the y part, which is which is 1, no 0, sorry, hang on. So y over x minus 2. So the I disappears, right? We don't need the I. So just do the imaginary component, which is just y, and then the real component, which is x minus 2. That's going to be tan of pi over 4, which would be I'm in degrees here, in radians. Tan of pi over 4, which should be 1, right? Yes, 1. Therefore, y is x minus 2. So now we've got two equations simultaneous, so substitute one into the other. Therefore, x minus 1 squared plus x minus 2 minus 1 be x minus 3 squared is 9. So this would be a quadratic for x. Therefore, x squared minus 2x plus 1 plus x squared minus 6x plus 9 equals 9. Therefore, x squared, 2x squared minus 8x plus 10 minus 9 plus 1 equals 0. Therefore, x is what? That's interesting. X is 4 plus or minus root 14 over 2. Well, that's helpful. Yeah, hang on. I think I've rushed too hard here. Let me check this again. So y over. Yeah, that's right. Y is x minus 2. Okay, but I must have expanded it wrong then. Hang on. X minus 1 minus 2 is minus 3. X squared minus 2x plus 1 plus x squared minus 3x minus 6x plus 9 is 9. So then 2x squared minus 8x plus 1 equals 0. So what am I getting to? I'm not getting the values that they've got. Hang on. That's weird. Well, there would be two solutions, wouldn't there? Look, the first solution would be there and the other solution would be there. Does it give us any value, any more information? No, it just says it satisfies this. So I guess we work with the fact there's two solutions then, I guess. So if x is that, x is 4 plus or minus. Actually, I'll do some of it here, actually, to be clear. So I'm going to continue this here. So x would be 4 plus or minus root 14 over 2. Therefore, y would be well, y is x minus 2. So that's going to be 4. Oh, sorry. And that's all over 2, by the way. There we are. And y would equal 4 plus or minus root 14 over 2 minus 2. Okay. So we have two possible numbers. So W1 would be 4 plus root 14 over 2 plus 4 plus root 14 over 2 minus 2i, or 4 minus root 14 over 2 plus 4 minus root 14 over 2 minus 2i. Okay, because that comes from y is x minus 2, just to clarify. So really it's asking us to find the modulus of the numbers, right? So W1 squared would be 4 plus root 14 over 2 squared plus 4 plus root 14 over 2 minus 2 squared, right? That's the square of the x and the y components. So if you do that, that would be so it's like no, that's not right. Hang on. Two plus or minus. Oh no, it is right. Hang on. We can simplify this, by the way, to say that x is 2 plus or minus root 14 over 2, right? So therefore y would be 2 plus or minus root 14 over 2 minus 2. That would cancel to just simply root 14 over 2. I'm doing this, by the way, because the calculator isn't giving an exact value, which I think is because we need to simplify this. So root 1, just to simplify, would be 2 plus plus root 14 over 2 plus root 14 over 2. And then W2 would be taking the negative version. 2 minus root 14 over 2. And then y would be minus root 14 over 2. So all I'm doing here to clarify is to simplify this. It's the right answer. It just the calculator needs to simplify it a little bit because it's a bit too complex for the calculator to work out to give an exact answer. So hopefully now we should be in a good position to evaluate the modulus. So 2 plus root 14 over 2 squared. Plus root 14 over 2. That would be, okay, let's try that again. 2 plus. If not, we can do it by hand. Although it would be a bit of work. Still giving us a bloody. Okay, we have to do it by hand. How annoying. Okay, we're gonna have to. You know, the mark scheme's cheeky. It just it jumps right from this to the answer. But the calculator, at least my one, the class whiz, isn't simplifying this. We have to do this by hand again. So we are going to have to simplify it to make it easier. But we're going to have to expand it. That's all we can do. So, the modulus of that's going to be 4 plus root 14 plus 2 lots of if you expand that's 4 plus 2 times root 14 over 2 times by 2. That would be 2 root 14. Plus the square of root 14 over 2. It should be 7 over 2. Oh, no, no, no. No, 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 no. That's why. I'm an absolute idiot. It's asking for W1 squared. Sorry. W squared, you're just removing the square root. So simply, you're just working out that. Oh my god, I'm a plum. So 2 plus root 14 over 2 squared plus root 14 over 2. That will give you 11 plus 2 root 4. There we go. Likewise, W2 squared, we need to check that should be the same. That would be 2 minus root 14 over 2 squared plus minus root 14 over 2 squared. That will be 11 minus 2 root 14. Oh, oh dear. So what did it say? What did the question say? The complex satisfies equals 3 and pi over 4. Oh, well, there's only one solution. Of course there is. It's here. Oh, yeah, so okay, that's why. Because I remember the reason why you get two solutions, that's really clever actually, is because obviously pi over 4 would be here, but if you continue the line, the other solution would be there. But that's not where our region is. So we need to ignore the solution with the negative the xy solution, right? The negative imaginary solution. So we need to accept the positive one. That's so. There's only one solution there. Oh, that's a really good question. That is okay. There we go. Okay. But solution lies in positive quadrant, right? Therefore, W cannot be equal to W1. W2, sorry, because W2 is the negative Y value, the negative imaginary. Therefore, W equals W has to be W1 only. Therefore, mod W has to be 11 plus 2 root 14. That's a really that's more clever. Oh god, that's a clever question that is. Okay, so let's go over that once more then to be succinct. So it's asking us to find the solution that satisfies both. If you put it like I did, did all the work in the calculator, you'd get two solutions. But think geometrically, if we continue this line on, because bear in mind this is the line y is x minus 2, continue the line on and then we'll intersect this circle again. But this is not in the region. Only this point here, which will intersect the circle here, is in the region. So that's the only solution here. So you need to reject the one with a negative imaginary value only and the positive stuff instead. Okay. Hopefully that's clear. And then the methodology is the same. So use x, convert to Cartesian, and then form a circle equation and a line equation, a linear one, and then substitute to solve. But reject the solution that does not lie in the region. Okay. Okay. There we are. Not, it doesn't have to be in the region necessarily here, but remember the half angle pi over 4 is only measured from the positive real. You do not continue it down, okay? So that's where you get the other solution if you continue the line down. So implicitly, this line only starts when y is 0, right? Implicitly, well, wherever your initial point is, right? That's where it starts. You don't continue it down. You start that. You would ignore the solution down here. Only this solution. Hopefully that is clear. Okay. Uh, Even I got stumped on that. Well, that's a really good question. That is. So there you go. That's how you tackle that. Two more questions now. I want to try whiz through it. Part A. So again, it's a serious question. Result. Use the standard results for r squared and r to show that. Well, we're going to need, like with usual series questions, we're going to need to expand, right? So 3r minus 2 squared. Actually, I'm going to do it in here, actually. Here we are, question 8. 3r minus 2 squared between n and r is 1. That's going to be the same as if we expand it, 9r squared minus 12r plus 4. Is that the right? What did I copy? Yes, I copied it down. Right, nice. So then really, if we split this up to say it's 9, lots of n and r is 1 r squared, minus 12 between n and r is 1 of r, plus 4 lots of 1 n and r is 1. And then you remember r squared is 9 lots of a 6 n plus 1, 2n plus 1. That's in the formula book. Minus 12 lots of a half n plus 1. That one you do have to learn. Plus 4n, because you add in 1 n times, right? So it'll just be n. Okay, now we just need to simplify this. So that's going to be 9 over 6, which is 3 over 2, n plus 1, 2n plus 1, minus 6n, n plus 1, plus 4n. I notice we can take a factor of n out. So that'd be left with n of 3 over 2, n plus 1, 2n plus 1, minus 6n plus 1 plus 4. Uh, okay, what does the question say? Okay, we need to have a quadratic in here, and we need to pull a factor of a half out. So then let's pull, actually, no, let's expand first. So it'd be n of 3 over 2, lots of 2n squared, plus 3n plus 1, minus 6n minus 6 plus 4, and that'd be n of 3n squared plus 9 over 2n plus 3 over 2, minus 6n minus 2. And then we can simplify it. So 3n squared plus 9 over 2n plus minus 6. So that'd be minus 3 over 2. And plus 3 over 2 minus 2. That'd be minus a half. And then you can pull out actually, it probably make more sense to write it here, wouldn't it? And then you could say that's half n. We can bring a half out. That'd be 6n squared minus 3n minus 1. And that should be the quadratic they want you to. That should be the expression they want. Yes, it is. Then it says, hence find for any positive values of n, such that this between n and 5. Let me get this down. Part B between 5 and r is 1 of 3r minus 2 squared. So what we just did. plus 103 between r is 1 and, was it 28? R cos r pi over 2. And I think it's equal to n cubed, right? R pi over 2 equals 3n cubed. Oh, okay. Okay, so, yeah, to do like to do this in series questions, throw in like a bit of an unusual bit to it, but it should be fine if you take your time. Well, not take it. Well, you should take your time, but I guess just consider it more carefully. But anyway, so this is between 5 and 1, the first part, and that is our between 5 and n. Sorry, that's I thought it was a bit weird. You can just add the first 5 terms. So between 5 and n. So that is going to be the same as this first sum here. So let's deal with the first sum. N and r is 5. 3r minus 2 squared, that's going to be the same as between n and r is 1, minus between r is 4 and r is 1, of the same thing, right? And then that's going to be, well, this sums from 1 to n, and that's what we've got here. That's why we're rewriting this, to get from 1 to something, right? So let's substitute 1 is n in here, so that's going to be half n, 6n squared minus 3n minus 1, minus, and then substitute 4 in for n. So that's going to be 4 over 2, that's going to be 2 lots of, and then we substitute, we're going to substitute n is 4 here, so that's going to be 6 of 4 squared minus 3 of 4 minus 1, that'd be 83. And I guess that would just be a half n, 6n squared minus 3n minus 1, minus 166. And there's not more we can do here. Now we're going to look at the second sum. So, this r bit, so 28 and r is 1 of r cos r pi over 2. Now, there's no, obviously that's an unknown, that's an unseen series. We don't know how to deal with that directly. So, like with normal math, the best way is to write down the first few terms, right? So the sum of that's going to be, sub r is 1. That's just going to be cos uh, cos of pi over 2 plus 2 cos pi plus 3 cos 3 pi over 2 plus 4 cos 2 pi, and then so on. And that's going to equal 0 plus minus 2. And then 3, that's going to be 0. And then that's going to be plus 4. And what do you notice here? Well, if we want to know your values, right, just look at the cos graph. Well, cos pi over 2. So pi over 2 is obviously here. That's like that's 0. Then pi would be minus 1. And then the next multiple of pi over 2 would be here, which is 0. And then 2 pi gets us 4, so 1. Okay. Now, actually, you should notice the pattern then because of this. So it's going to be 0 minus 2, plus, then plus 0 again. Because again, it's going to dip down like this to 0. Then you can have a negative. But then it's going to be 6. So that's a sixth term. And then plus 0, plus 8. And then plus 0, minus 10, plus 0, plus 12. And so on until the 28th term. And the 28th term would be... but substitute 28 in, so that's going to be 28 28 cos 14 pi, right? 28 pi over 2 with 14 pi. That would give us plus 28 at the very end. Now, actually, you should notice a pattern here. And what we can say is, That's good. Well, we can say that's equal to -2 then, get rid of the zeros. -2 plus 4, -6 plus 8, -10 plus 12, plus 28. Now, what's happening here? Well, actually, it's kind of like a method of differences. So the 4 would cancel the -2. So you could say 4 minus 2 plus 8 minus 6 plus 12 minus 10 plus dot 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 plus obviously then 28, which is positive, minus 26. And we can group them into pairs where they give us 2. So that's going to be 2 plus 2 plus 2 plus dot 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 plus 2. Now, how many pairs are there? So we're adding 2. Well, it's going to be 14 times, isn't it? So that's going to be 14 lots of 2. You can see that because obviously, uh, uh, well, we only have every even number's included. Hang on, how do I want to say this? 1, 2, 3. Well, think about it, I guess. So we got to look at how many pairs. Obviously, it goes from 2 to 6 to 10. So 2 to 6 to 10 to 14 to 18 to 22 to 26. Also, there's 7 pairs and 7 times, sorry. So look to look how many pairs there are, kind of, I don't know, see how much it's going up by. So from 2 to 6 to 10 to 40. So 1, 2, 3, 4, 5, 6, 7 pairs. So there's 7 lots of 2 here, okay? So that should equal 14. I think that's where I got the 14 from. But that's how you can work that out. And so actually that whole series then just boils down to 14, which is great. So therefore, the sum is the first bit, which was a half n squared. I forgot to say a half n of not n, sorry, it's 6n squared minus 3n minus 1 minus 166. Add now it was 101, 103 lots of that, wasn't it? So it's 103 lots of 14, which is equal to 3n cubed. Well, if it's n cubed, we're going to have to expand it, aren't we? Unfortunately. We're going to expand this, so it's going to be 3n cubed, which is great because that will cancel. Minus 3 over 2n squared minus a half n. Now we can deal with this constant here. Minus 166. Add 103, lots of 14. That gives us 1276. Minus 3n cubed is 0. But the n cubed cancels, so you can be left with minus 3 over 2n squared minus half n plus 1276 is 0. And now this is quadratic, so that solves 2 if you used your calculator. And you should get an even integer value for p, so that's minus 1.5, minus 0.5, and 1276. And lovely, you get n is 29, or n is minus 29.33. N is positive, obviously, and an integer. So n is 29. Is that the solution I wanted to find the value of n? Uh, it is, yeah. Find any value of n. There we are. So that's how you approach that question. Lovely, lovely. So, like as I said, if you get an unknown series like this or whatever, again, try and break it down. Even list the terms if you need to see what happens. But yeah, that's series. And now this is the final question. I could leave it there. It's a bit late, but I will do this. I will make sure I do a coupled ODE question because it will come up as a lot of marks, and I don't want to leave anyone hanging. So all I'm going to do here is just copy. Actually, I'm gonna Okay, I'm going to do it on the left side now. Hopefully it's not too confusing. So what I'm going to do is copy the two differential equations because that's all we're going to need. It's a load of waffle, right? But we're given dw by dt, and I picked this question for a particular reason, and you'll see why in a minute. So dw by dt is 5 over 2w minus s, and the s by dt, that's going to be 2 over 5w minus 90 e to the minus t. Okay, so essentially we need to show this, okay? So if you look at here, this is very common for coupled questions to show that first. So we need to get it in terms of dw by dt, in terms of w, right? We don't want any s's. So the way to approach this is firstly to, oh yeah, can't even speak now, is to notice, well actually, we have a d squared term here. There's no like, a second derivative, sorry. Well, there's no second derivative we can get from here, so we're going to have to differentiate, and we're going to make sense to differentiate this, right, to get d squared w, which is here. So that's our approach here. So if we differentiate dw by dt, if it's 5 over 2w minus s, we get d squared w by dt squared, and that's 5 over 2 dw by dt. Now it's not 1, you don't differentiate w, you're differentiating t. So it's simply dw by dt, and it helps to remember that with these questions, that in a way, they're kind of like parametric equations. I kind of like calling this parametric differential equations because essentially w is a function of t and s is a function of t. It's a different function of t. And t is a parameter here. So it's kind of like parametric differential equations. So they're both functions of t. So if we differentiate w with respect to t, well, that's just dw by dt, right? Or f dash of t. We are basically, the whole idea is to find these two functions. So we get w and s just in terms of t, defined almost like the parameterization. That is the whole idea here, okay? So they're initially coupled, but we kind of want to decouple them to get w in terms of t alone, outside of s and w. But anyway, if that helps you make it understand why, it's dt here, not just 1 to differentiate w. W and s are functions of t, so we need to just do the first derivative, right? And likewise, this will be minus 5 to ds by dw by dt, the function of t, right? So that's great. Now, actually, we know what ds dt is just in terms of w. So I think we could substitute ds by dt in. So let's see what happens. So d squared w dt squared. Oh, hang on. That's going to be 5 over 2 dw. Can't do anything more with that. Minus 5 over 2. Now, ds by dt is 5 over 2 of 2/5. So that's going to be minus w. And minus 5, 5 over 2. Lots of minus 90 e to the t. So that's going to be plus 225 e to the minus t. And that's all in terms of w and t. So it's a differential equation, but you can solve for w. Now we need to make it all on the left. We need to rearrange this. So let's have a look. How should we rearrange it? Let's look at the question. Okay, all the w's on the left and the e to the minus t is on the other side. Okay. So that's what we're going to do. So d squared w dt squared minus 5 over 2 dw, w dw by dt, sorry, there we are. Minus w, no, plus w equals 2 to 5 e to the minus t. Okay, now we want to get rid of this fraction. If you notice, it's 2 lots of d squared w in the answer, so let's times by 2. So that means we get oh god, here we are. 2d squared w by dt squared minus 5dw by dt plus 2w is equal to 450 e to the minus t. There we are. Is that the answer they're looking for? Hopefully it is. Yes, it is. Great. So that's part A. So the tip with this to show that uh, you're going to want to differentiate the variable that they're interested in. So W here, differentiate the equation with W. They should be quite clear because there's no way you can get a second derivative without differentiating. Okay. Now it says find the general solution for W, essentially. So really just solving this second order ODE. So first of all, we need the auxiliary equation. So that's going to be 2m squared minus 5m plus 2 equals 0. So that as the solution. Put that into the calculator. 2 minus 5 and 2 gets m is 2 and m is a half. So therefore the what's it called, the complementary solution, or the complementary function. So the complementary, if I can write this, or the complementary solution, whichever way you call it, the complementary function, you could just call it CF or CS, whatever you prefer. That's just going to be W is e to the so it's e to the e to the 2t a e to the 2t because it's a general one, a to the 2t plus b e to the half t. Okay, so you need to remember that when you have two real roots distinct, it's in this form. So it's a general unknown constant by e to the root t plus b e to the other root t. Okay. Um, and I guess the reason that works is because e to the t is the only thing that remains the same. Because d to the dt of e to the x, or e to the t, is still e to the t, right? So if you differentiate this once and twice, it will what's it called? It will because obviously this is solving. What this is doing is solving the differential equation when it's equal to 0. So the fact that e to the t or e to the x remains the same under differentiation is why this works here to give the complementary solution. Anyway, I'm going to stop waffling there. I'm going to leave it there. So that's complementary. Now we need a particular integral. Now, our particular integral, or PI, or what I'll call the CF, that has to be of the form W is, it's going to be lambda t e to the minus t. So normally, if it's just e to the minus t, it would look like lambda e to the minus t. But we have we have something here, right? We have our complementary function looks like this, right? It has a term that looks exactly like this, right? So when that happens, what you need to do, if you remember, you need to tag a t on, and then this is distinct from the other solutions, okay? Because the whole idea is for to give a solution to this part here. But if this is the same, then it will actually solve 0 instead. So we need to make it distinct. I won't go too much in detail. That that's sort of the idea, but I'm not going to go into detail about differential equations now. I just want to solve it. Okay, go over the method. Um, do, 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 do. Yeah, so that's what we're going to try. So that means W is equal to this, remember? So that means if we need to essentially substitute W into this equation and then compare to e to the minus t here. Okay, and that's why we need it to be different, because if it was the same as a complementary function, you just get it equal to 0. That's not what we want here. We want it equal to some 450 e to the minus t. So when we are comparing, it needs to be distinct to the complementary, okay? Anyway, so that's e to the minus t. Therefore, w dash is going to be minus lambda e to the minus t, and w dash dash would be lambda e to the minus t, right? Times by minus 1. Therefore, sub pi into the ODE, you're gonna get, and this is the method of solving inhomogeneous ODEs, by the way. This should be a refresher course, hopefully. Should have hopefully comfortable with this. But this is going to be 2 lambda e to the minus t minus 5, well, minus 5 of minus lambda, so it's plus 5 lambda e to the minus t, plus 2w, so that's going to be plus 2 lambda e to the minus t. No, it's t, sorry. No. I didn't even see the t there. What's going on? This is product rule then. So w dash, so that's going to be differentiate t first. So that's going to be lambda e to the minus t plus minus lambda t e to the minus t. And then w dash dash is going to be, and then we need to get this out. I didn't see the t there. I just thought it was lambda e to the minus t. So we need product rule here because it's two functions of t. That should be right. And then w dash dash again. That would be minus lambda e to the minus t. And then apply the product rule here. Minus lambda e to the minus t, differentiate the t bit, and then differentiate the e to the minus t. So that's going to be plus lambda t e to the minus t. We can simplify this, can't we? So then that means w dash dash is going to be minus 2 lambda e to the minus t plus lambda t e to the minus t, okay? Let me check that. Is that right? Minus lambda, minus. Okay, that should be okay. Then I'm going to substitute this in. So the w and w dash and w dash dash. So two lots of second derivatives can be um, minus 4 lambda e to the minus t plus 2 lambda t e to the minus t. And then minus 5 w dash. So it's going to be minus 5 lambda e to the minus t plus 5 lambda t e to the minus t. And then plus 2w, well, w is just that, plus 2 lambda t e to the minus t. And that's going to be equal to 450 e to the minus t. Okay, so what do you do here? Well, actually, we can simplify this a bit, can't we? Let's group these terms together. So let's get all the lambda t terms, right? T e to the minus t, 2 lambda plus 5 lambda plus 2 lambda. That's going to be 9 lambda t e to the minus t. And then minus 4 lambda, and then e to the minus t terms on their own. Minus 4 lambda minus 5 lambda. That's going to be minus 9 lambda e to the minus t. It's going to be 450 e to the minus t. Uh, Oh, hang on. Ah, no, we're fine. Yeah, okay. You won't get a solution here. Um, it won't be possible because obviously you'll just have to say that this bit would be 0. So lambda would have to be 0 to ensure that there's no t e to the minus t. So then that would be 0, but then it has to be 450 e to the minus. So that's wrong, and I'll explain why. You don't need to tag a t on. Okay, this is a good refreshers course for me as well. I haven't done this in ages. So you're probably screaming now, and rightfully so. So you only need to tag a t on when it's the same exponent. I just realised that now. I thought it had. So you can just say w is for a particular integral lambda e to the lambda minus t, because minus 1 is not in the exponent, so it'll still be different to the complementary function. Okay, I do apologise about that. But I can see I was wrong though. I guess it didn't take too long to do all this. I don't know, but still not ideal. God, yeah, I haven't done these in absolutely ages, in years actually. I got the general method, but I'm still getting a bit used to it. But this is good, right then. See, we're still ironing out any potential like issues, right? But anyway, hopefully you should have realised that. It's good revision. Anyway, so really, it's the first. Yes, what I did before, right? First time. So w dash is simply minus lambda e to the minus t. W dash dash is going to be again lambda e to the minus t. Substitute that in. You get well, 2 double dash that's be 2 lambda e to the minus t minus 5, that's be plus 5 lambda e to the minus t plus 2 lambda plus 2 w, sorry, so 2 lambda e to the minus t equals 450 e to the minus t. Okay, and so that simplifies to 9 lambda e to the minus t is 450. There we go, it's much nicer. Therefore, we can compare to say 9 lambda has to be 450, which means that lambda is 450 over 9 equals 50. Okay. So to clarify again, with particular integrals, if it's exactly the same, if you had a e to the minus t, so minus 1 was the root, then you would have to tag on a t. But yes, they look similar, but the exponents are not the same. So you don't have to tag on a t, okay? Say like again, I know one of them could be like sine of 2t. Say like if one of the complementary functions is in the form a sine, and then you had a what's it called, a right hand side equal to another lots of 2t, right, sine 2t. Then again, you would need to change this particular integral to be a t sine or something. You know what I mean? I believe anyway. But yeah, so because the exponents are not the same, then it's still different. Okay. Okay. Hopefully that clarified. So now we got our lambda, so therefore particular integral is going to be simply 50 e to the minus t. So therefore our general solution is our particular integral. So it's a complementary function plus a pi. So a complementary function, remember, was ae to the 3t, was it? 2t. Okay. Plus be to the half t plus 50 to the minus t. Sorry. Okay. Uh, Great. So that's the answer to that. So that's the general solution for W. So that's W equals. So now it's saying um, to find the general solution for the crayfish. That is S, right? Crayfish is S. So that's only 2 marks, but we need to remember that we can use our original function here. So we know here. So the first equation, we know that 5 over. I'm going to write this again. dw dt is 5 over 2w minus s. We have s there for us. So 5. So I'm going to say again. dw by dt is 5 over 2w minus 5 over 2s. Okay, and that comes from the first equation, right? So again, you use the first equation, then you can find s to find a general solution for that. Um, so really, we need to substitute w, dw, and w in. So dw by dt, so w is that, remember? So dw by dt is going to be 2a e to the 2t plus a half b e to the half t minus 50 e to the minus t, right? So if you sub w and dw into first equation, which was obviously the this bit here. You can call it equation 1 if you want to. That's going to mean, well, actually, I think it's good to rearrange for s, right, before we put the numbers in. So 5 over 2s is going to be minus dw by dt plus 5 over 2w. Or therefore s would be, if you divide by 5 over 2, that would be w minus 2/5 w, dw by dt. Then we can substitute that in directly. So don't, so yeah, substitute for, rearrange for s first before you plug the numbers in. Because once, because once you substitute all this in, then if you want to rearrange for s, it gets a lot messier. So let's do it first, and now we substitute for w and stuff. So w, remember, is a e to the 2t plus b e to the minus a half t. Right, was it minus a half? No, it's just a half. It looked like minus a half. Anyway, that's b to the 2t, half t, plus 50 e to the minus t. And then we need to minus 2/5 the derivative, so that's going to be minus 4/5 of a e to the 2t. Then minus 5 over 4. No, 2/5, sorry. So that's just going to be minus a fifth, right? Fifth times in minus 2/5 over here. Minus the fifth b e to the half t. And then minus 2/5 times minus 50 e to the minus t. You get plus 20 e to the minus t. We can simplify this, right? So that would be a minus 4/5 a. That would be a fifth a e to the 2t. be minus the fifth b. That becomes 4 over 5 be to the half t. And then 50 plus 20 plus 70 e to the minus t. Okay. Lovely. So that's for 2 marks. Fairly simple. So now we have a general solution for the s and the w. But now we need to find a particular solution, and we got given some values, right? So the model predicts that at time t, the population of so t is t, the population of white crayfish, so that means S, is died out. So S represents the population of crayfish, remember? Uh, oh no, white clawed crayfish. Sorry. So the white clawed is W. There we go. W is 0. If they died out, that means there's none left. And we're also given this boundary condition, W is 65, S is 85. So let's write that down. That will allow us to find a particular solution, so then we can use our equations to find other values. So we can find this T here. So this is our boundary values we need first. So we need W is 65, S is 85, T is 0. So C, W is 65, S is 85, and T 0. So sub W65 in and T 0. We'll sub that the W into the W equation. So remember our solution for W was here. So that means 65 has to be, well, A e to the 0, so that's going to be A. Plus B e to the 0, that'd be B. Plus 50 e to the 0, that'd be plus 50. And that means A plus B has to be 15, right? And then we're going to substitute S is 85 and T 0 into our solution for S, which we found. That's why we wanted us to work out W and S, right? All these coupled first order ODEs are exactly the same. If you should know how to solve second order ODEs, please learn how to do coupled first order. They are worth so many marks and they really help you out. They guide you. I don't know. There's a lot of marks you can easily gain. That's why I'm taking the time to do it now quickly to show the general method, right? But anyway, T0, so that means 85. That's going to be for S here, so that's going to be a fifth A plus 4 over 5B plus 70. And then that means a fifth A plus 4 over 5B. That's going to be 15, right? Again. Okay, now we can solve them simultaneously. So A plus B is 15, 0.2A and 0.8B is 15. So that means I'm going to need another paper here. Let's try this. Okay, I'm going to need another page here. There we are. Okay, so if you solve them, that you get A to be minus 5, okay, and B to be 20, okay. So that means W then, if you complete it, so W, remember, was up here, so it's A e to the 2t plus B e plus 50 e to the minus 2. So it's minus 5 e to the 2t plus 20 e to the half t plus 50 e to the minus 2, was it? Yes, it was. Okay, cool. And that means S then as well. Well, actually, we don't need S because what we then want to work out is, because we know our values now, we want to find, if you remember the question, we want to find the value of T when W is 0, right? So W 0 means that 0 is minus 5 e to the 2t plus 20 e to the half t plus 50 e to the minus t. Okay. Okay, interesting stuff. So this now we are expected to solve this. This kind of reminds me of what's it called, of a hidden quadratic, right? But how do we solve this? Well, um, usually with hidden exponential quadratics, you should be, I think, yeah, in the hyperbolics chapter, you should be quite familiar with hidden quadratics. Could you use them to solve various hyperbolic equations? Because obviously hyperbolics are in terms of exponentials, so you can apply it here. But usually the method is to times by an exponential power to make one of them a constant. And I think the best way is to get rid of this e to the minus t. So what I'm going to do is times both sides by e to the minus t and see what happens. So you can get 0 is e to the 5 minus 5e to the minus t. No, t, sorry. 5e to the t minus 5e to the t, because you're subtracting the power, times in by e to the minus t, 2t minus t is t, plus 20e. Now half t minus t is going to be minus a half t, and then plus 50. Um, okay. Uh, hmm. Okay, it's not apparent here, but perhaps, maybe instead, because we got rid of one number, uh, no. No, it looks vaguely similar. If we say this is e to the half t to the minus one, then that would, if we that be e, that's e to the e to the t to the square of that. So we have like an x squared and an x term, like a u squared and a uh, but it's by minus one. Hmm. Okay, let's instead try times by e to the minus a half here maybe. So then 0 would be minus 5e to the well a half. Plus 20, plus 50e to the minus a minus a half t. Well, actually, we're in a much better position now because they're just opposites, right? Uh, so now, let's again times by e to the half t now, and then you get 0 is minus 5e to the t again, plus 20e to the half t. So not minus half, now we've got half t, plus 50. But how shouldn't this have been? Ah, and that's weird. So that's saying e to the half is the same as e to the minus a half. Have I done this right? Hang on, let's have a look. Oh no no no. Oh. No, because I'm timesing by e to the minus. No, I was meant to divide by e to the minus t. Sorry. There we are. Let's go back. That's what. Yeah, I should. Yeah, not you don't want to times by e to the minus t. Sorry, but you can times by e to the t, right? I think that's what I was meant to do because divided by e to the minus t is the same as times by e to the positive t. So divide by e to the minus t. So then that will go to a constant. There we are. Because I timed by e to the minus t. That should have been e to the minus 2t if you add it. That's not what I want here. Okay, so 0 would be 5e to the t now. No, if you're dividing, it'd be 3t, wouldn't it? Because e to the 2t divided by e to the minus t. That's, you are subtracting the powers, but 2t minus t would be 3t. Likewise, this would be 20 e to the 3 over 2t. Because you're adding 1, and then that would go to 50, because you're adding t here. So that's our equation, right? But actually, this is now a hidden quadratic. Because notice it's the same as saying, well, I'm going to rewrite this a bit slightly. This is the same as saying 5e to the, no, sorry, 5 e to the 3 over 2t squared, because then you times 3 over 2 by 2 to get 3t, plus 20 e to the 3 over 2t, plus 50 equals 0. Is that not a hidden quadratic where u is e to the 3 over 2? I think it is. So I think now this is quite nice to solve. Therefore, e to the 3 over 2t, if you plug the quadratic 5u squared plus 20u plus 50 equals 0 in the calculator, what values do you get? 5, 20, and 50. Oh. Well, you get complex roots, actually. That's not ideal. Because this is minus 5, that's why I forgot a negative. So that's minus 5, so plug minus 5 into there. And hopefully get a nice number now. There we go, it's 2. 2 plus root 14, okay? You get 2 plus or minus, but the 2 minus root 14 is negative. But that can't happen because if you remember, e to the anything, you remember the graph of e to the x, is always positive, right? And even if you didn't realise that, eventually you'd get either t would be negative for negative time, which can't happen, or it'd be undefined when you do a logarithm. But anyway, this is solution if you realise that one. Therefore, t, well, 3 over, well, if you log both sides, 3 over 2t, if you ln both sides, ln of e to the 3 over 2t, so that's 3 over 2t ln e, which is 1. So 3 over 2t is ln of 2 plus root 14. Therefore, t is 2/3 ln 2 plus root 14, which is which is 1.165 something. Is that in years? In year, okay, that makes sense. In years, okay. So it's 1.165 years, right? And so the final, that's the whole question, right? Lovely. So that's big T, I should probably say. That's the value of big T. So then part C, again, part D, give a limitation type of question because it's a modelling one. And so a limitation of the model, well, again, if it's a limitation of a function like this, consider if it goes to negative, right? So look at this W and S here. Does it ever be negative? Well, get W and S can't be negative. Well, actually, no, we have a negative coefficient here of A. So, for example, W here is -5. So, really, it's going to be negative if you think about the graph e to the x. If E is very small. No, yes, very small, such that e to the 2t would dominate more than half t and minus t. Well, actually, we have a value of t here. So for w, we know it goes to 0 when w is 0, when t is this 1.165 that we worked out. What happens when t is bigger than 1.165? Let's try it out. Are there any negative values? Let's try, I don't know, minus 5e to the 1.2, for instance. So 2 times 1.2 plus 20e to the 0.5 of 1.2. So substituting t 1.2 to see if there's any negative values to give a limitation. So plus 50e to the minus 1.2. And you get a negative value, right? So the model predicts that, say we substitute, and you can use this value to guide us here because this is when w is 0. Obviously, think about a graph. I don't know, something like this. I don't know. When you go w go to 0, it can be near the values of x, the root, right, or t even. So say this is w and t. It can either go positive if you go to the left of t, or negative to the right or left. So test values of t around the point where it's 0 to see if it's negative. But actually we do. So if say we substitute t is 1.2 into w, we get w negative 3.61. Which is obviously, and that's the kind of aim of this. A limitation is to work out if it predicts negative values. Obviously, it shouldn't, so that's a limitation. So we get w, which is minus 3.61. So therefore, model predicts negative, like negative population, right? Population numbers. Because obviously that's what W represents, the number of like clay fish or something like that. Predicts negative population numbers, which is nonsensical, hence a limitation of the model, right? So it says either population becomes negative, which is not possible. So that's kind of what we said there, right? When the when the white crayfish has died out, the model will no longer be valid. So yeah, so when t is bigger than this 1.165, then apparently the model goes into a negative. So apparently you get negative volume amounts. Anyway, that's the whole paper done. There we go. We got there. We got there. I am going to leave that there. I will stay around for a second. Let me check the chat. Hopefully it should be okay. I'll stay around here for like a minute or so. If there's any questions coming in, but that is essentially what I wanted to go over. These are the questions, um, the topics anyway that will come up. Hopefully they're quite similar questions as well. Hopefully, you never know, but I think you'll get very good practice if you watch today and yesterday's stream for your revision. But yeah, so these are the sort of predicted topics. Obviously, we can't predict the questions exactly, but we have a good idea of the topics anyway. So this will be very good practice for tomorrow, right? Um, so I'll just scroll the questions once more. Uh, okay, let me get rid of this so you can see clearly what's it saying. There we are. Okay. By the way, to note, if you pause the stream, you can attempt the question with the paper, and you can see the mark scheme as well. That's why I labelled where the question came from. Proof by induction. And yeah, and these are the predicted topics. So I'm going to leave it there for like a few seconds. Let me scroll back. There we are. But yeah, you can see we went through them all, right? So we did the this was the linear transformation question. Uh, the first one. So we did that one. We did a vectors question. We kind of did two in a way. Can you remember the system of equations question? That was linked to vectors. We did a proof by induction one. We did a polar one. We finally did a coupled one. We did a series one. We did an Argand with Loci. We did a roots one. The only one we didn't do was a Maclaurin series. We did do one yesterday, but obviously I didn't want to spend much time, more time than I already have. And the Maclaurin ones are usually quite standard. They're not worth many marks, so hopefully that should be okay. But that will come up as well. But we practice all these major topics today, so hopefully this stream will be of use. And it looks like there's nothing there, so I am going to leave it there then. I am going to endeavour to put this on my YouTube as well. So obviously for the exam, hopefully it should be on tonight. Hopefully, but YouTube and Twitch could play up. But hopefully this will be on value. Also to reiterate, Tuesday, yesterday's stream and vice versa. They're both good. I think they're both good resources for predictions, right? Um, so make sure you have you practice the breadth of various different topics to get a good breadth to be well prepared for the type of questions that could come up. But I'll try and answer any questions, say if they come up in the comments or whatever before your exam. But other than that, I am going to leave it there. So thank you.